When astronomers first detected the object now designated 3I/ATLAS, the details seemed straightforward. A small speck of light captured by a survey telescope in Chile, another data point in a nightly routine of scanning the sky. But very quickly, what appeared ordinary began to unravel into something unprecedented. Calculations of its orbit revealed a hyperbolic trajectory, the unmistakable signature of an interstellar visitor. It was the third time humanity had confirmed such a wanderer, following the discovery of 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Yet there was something different about this one. From the beginning, 3I/ATLAS refused to behave like a typical comet or asteroid, forcing scientists to question not only its composition and origins, but what its arrival might imply about the nature of our universe. At face value, interstellar objects are not impossible. Planetary systems form in chaotic environments where gravitational encounters fling debris out into interstellar space. Some of that material should, by probability alone, cross paths with our solar system from time to time. But the first three detections raise questions about just how frequent these encounters should be. For decades, astronomers predicted that interstellar objects would be rare, maybe once in a century discoveries. Yet within less than a decade, 3 have appeared, each with unusual characteristics. It's a small statistical sample, but enough to make researchers wonder if something more than random scattering is at play. The first was elongated and oddly reflective. The second looked more like a traditional comet, but still carried mysteries in its chemistry. Now the third arrives faster, richer in carbon dioxide, and traced back to a stellar population as old as the Milky Way itself. The question grows sharper. Why do these visitors keep arriving in ways that stretch natural explanations? And if this third one is not entirely natural, what would that mean for us? From the start, astronomers noted 3I/ATLAS's extreme velocity. Its hyperbolic excess speed exceeded 60 kilometers per second, far faster than most interstellar objects should travel if they were ejected through ordinary planetary interactions. The fact that each successive object we've detected has come in faster than the last pushes the boundaries of coincidence. Could it be that we are simply glimpsing the higher end of the speed distribution, or is there an underlying pattern? Patterns in astronomy often signal hidden mechanisms, and hidden mechanisms sometimes lead to unsettling conclusions. But speed alone isn't what set this visitor apart. Its spectral analysis revealed chemical signatures unlike anything in our solar system. The James Webb Space Telescope identified an unusually high ratio of carbon dioxide compared to water vapor, at a scale unprecedented in cometary science. Such chemistry suggests formation in conditions very different from those around our Sun, perhaps in a region of a protoplanetary disk where carbon dioxide dominated while water ice was scarce. Yet the timing of its activity seemed suspicious. At distances where most comets remain quiet, Atlas was already active, expelling gas into space with energy that raised more questions than it answered. Astronomers naturally gravitate toward conservative explanations. Radiation processing, cosmic ray exposure over billions of years, the possibility of insulating dust layers shielding water ice while allowing carbon dioxide to escape. Each explanation has some merit, yet none feels complete, and so speculation begins. Because speculation fills the gaps when observation falters. Could this object be engineered to appear comet-like while carrying systems we cannot detect? Could its unusual composition be a deliberate feature, designed to mask its true nature under the cover of natural variance? The problem with dismissing such ideas is that history repeatedly shows nature-producing phenomena that mimic intention. Pulsars, fast radio bursts, quasars, all once seemed suspiciously artificial until further evidence revealed natural processes stranger than we imagined. But the inverse lesson also holds. When evidence fails to fit existing theories, the possibility of design cannot be excluded outright. A thought experiment emerges. What if the visitor we're watching is not random debris, but a reconnaissance device camouflaged as cometary matter? The worst-case scenario isn't collision or impact. It's that we fail to recognise the presence of intelligence operating at scales we cannot match. Consider the disguise hypothesis. If a civilization wanted to observe emerging species in distant star systems without detection, what better strategy than to mimic the most common natural interstellar visitors? Comets and asteroids number in the trillions. Their flybys generate no alarm. But if one were engineered to carry instruments, it could drift unnoticed past countless civilizations, harvesting information while blending seamlessly with cosmic background noise. The discovery of 3I/ATLAS invites us to entertain this possibility, not because evidence proves it, but because the consequences of ignoring it would represent the true worst case. What if this visitor is not leaving? The mathematics show a hyperbolic escape trajectory, but trajectories can be altered by subtle forces we cannot measure at vast distances. The idea that Atlas might use the flyby to decelerate rather than accelerate may sound like science fiction, but deceleration is exactly what any probe would require to linger in a system. A faint plume of gas misinterpreted as cometary outgassing could in fact be controlled propulsion. Anomalies too subtle for current telescopes might conceal deliberate maneuvers, and if its path does change in ways we cannot predict, how long would it take us to notice? There is also the matter of its origin. Backtracking its velocity vector places its source not in the orderly thin disk of the galaxy, where most stars and planets reside, but in the thick disk, a population of stars formed billions of years earlier. That makes Atlas potentially older than our solar system, a relic from a time before Earth even existed. If it is merely natural debris, it is a geological artifact beyond comprehension, carrying within it chemical records from the infancy of the galaxy. But if it is something more, then we are witnessing the arrival of technology designed by a civilization that predates humanity by billions of years. The implications of that possibility are staggering. Even if natural, its survival raises questions. Small objects should not last intact across billions of years of interstellar travel. Collisions with dust grains at high velocity should erode them. Radiation should gradually alter their surfaces until volatile activity becomes impossible. Yet Atlas has arrived vigorous, active, and still massive enough to generate a coma visible across astronomical distances. How does something so fragile endure so long? The natural explanations are unsatisfying. The speculative ones suggest durability born of design rather than chance. Our instruments report silence. No radio transmissions, no coherent signals, no thermal anomalies. Every dataset reinforces the natural hypothesis. Yet absence of evidence is not evidence of absence, especially when we are dealing with potential intelligence orders of magnitude more advanced than our own. A probe designed to remain hidden would not broadcast in ways we could detect. It would emit only what we expect to see from natural processes, staying quiet in the electromagnetic spectrum and obeying the visible laws of orbital mechanics. Its very silence could be the signature of success. This leads to a paradox. The more convincingly natural ATLAS appears, the more effective it would be as an engineered device. If we dismiss the possibility of intention solely because it behaves like a comet, we blind ourselves to the prospect of intelligence advanced enough to master the art of disguise. And if such intelligence exists, the arrival of ATLAS may not be a coincidence. It could be a deliberate encounter, timed for reasons we cannot yet discern. For now, humanity watches. Telescopes across the globe and in orbit continue gathering data, feeding it into models that confirm the natural interpretation again and again. But the shadows of speculation remain. What if the data we trust is exactly what was meant for us to see? What if we are studying not a visitor from the stars, but an emissary designed to watch us? The line between natural and artificial blurs when the stakes grow high, and the worst possible scenario is not impact, not destruction, but observation. To be observed without understanding by a presence beyond our comprehension may be the most unsettling outcome of all. From the very first orbital calculations, the numbers surrounding 3/ATLAS seem to carry a quiet menace. Objects in space move fast by human standards, but their speeds usually fall within familiar boundaries defined by the gravitational wells that shaped them. Asteroids bound to the Sun trace their elliptical paths at velocities that rarely exceed a few dozen kilometers per second. Comets, when accelerated inward from the outer solar system, can reach more than 50 kilometers per second near perihelion, but always return to the long, slow arcs that brought them here. Hyperbolic interstellar visitors, on the other hand, are different. They arrive carrying the momentum of other star systems, their paths open-ended, their fates unbound. With 3/ATLAS, that distinction becomes impossible to ignore. Its hyperbolic excess velocity of more than 60 kilometers per second makes it one of the fastest natural objects ever observed crossing our neighborhood. To put this in perspective, 60 kilometers per second means that every second, the object travels further than most commercial airliners cover in a full minute. In 1 hour, it crosses over 200,000 kilometers, nearly half the distance from Earth to the Moon. In a single day, it sweeps through more than 5 million kilometers of space. Compared to terrestrial experience, the figures lose all meaning. Even compared to other cosmic wanderers, ATLAS seems to move with unreasonable urgency. Oumuamua entered our system at around 26 kilometers per second. Boreloff managed around 32. The third visitor doubles both predecessors, suggesting that with each new detection, the velocities we encounter grow more extreme. Coincidence cannot be dismissed, but neither can the possibility that these increasing speeds hint at something larger than chance. When scientists simulate the scattering of small bodies during planetary system formation, they find that typical ejection speeds fall in the range of a few kilometers per second. To reach more than 60 requires extraordinary events, close encounters with giant planets in unstable systems, violent multi-body interactions, or ejection from binary star systems, where gravitational slingshots impart enormous energies. Any one of these explanations is plausible, but each grows harder to reconcile with the pattern of what we have already observed. How many times can we attribute unusual interstellar arrivals to extraordinary coincidences before we begin to wonder whether something else shapes their trajectories? The faster the object, the shorter our window to study it. Speed robs us of opportunity. By the time telescopes locked onto ATLAS, it was already inbound, crossing millions of kilometers each day, its perihelion date fixed and approaching with relentless certainty. Unlike planets and asteroids, whose motions allow us years or centuries of prediction, these interstellar visitors grant only fleeting moments. Oumuamua was discovered after it had already passed closest to Earth, leaving us chasing a receding mystery. Borisov gave us more time, displaying its cometary tail as it swung through the inner solar system. Atlas splits the difference, bright enough to study but too fast to linger. The pace of its passage forces us into accelerated science. Telescopes worldwide racing to collect as much data as possible before the object vanishes forever into the deep. The physics of such speed complicates speculation. At more than 60 kilometers per second, Atlas is immune to capture by the Sun. Its trajectory is hyperbolic, meaning it will not return. The mathematics appear precise, but the speculative mind notices something else. That speed is also optimal for reconnaissance. Too fast to be trapped, too swift to be intercepted by our spacecraft, its trajectory guarantees both escape and safety. A civilization deploying disguised probes would likely choose velocities that maximize data collection, while minimizing the risk of detection or interference. From our perspective, the object appears as a harmless natural comet. From another, it could be the perfect scout, gliding past planets, sampling radiation and emissions, observing without consequence before continuing its endless journey. High velocity, also provides durability. Collisions with interstellar dust grains, while destructive over billions of years, become less significant if the travel time is reduced by speed. A probe moving twice as fast spends half as long, exposed to the hazards of deep space, increasing its chance of survival. Perhaps Atlas moves quickly, not by accident, but by necessity. Perhaps the civilizations that built it, if any exist, understood that time itself erodes even the hardiest technologies. If the object is engineered, then its unreasonable speed is not a coincidence but a design choice. But speed raises other possibilities as well. Could ATLAS have been accelerated deliberately? Our own species has begun experimenting with the concept of light sails, thin sheets propelled by radiation pressure or directed lasers. In principle, such technology could drive small probes to interstellar speeds exceeding those of natural ejections. If even a young technological civilization like ours can envision this, then older civilizations might have mastered it long ago. The question becomes uncomfortable. Are we watching the flyby of an object accelerated across the galaxy by intelligence, camouflaged in cometary dress? If so, its speed is not evidence of chaos but of precision. Astronomers, cautious by nature, resist these ideas. The conservative explanation remains the simplest. A small, icy body, flung outward from its natal star system during chaotic early years, drifting for billions of years until chance delivered it to our doorstep. Yet the sheer velocity challenges this narrative. Computer models predict interstellar visitors should arrive in numbers consistent with random ejections, but at speeds somewhat lower than what we observe. Are we simply unlucky to have witnessed 3 unusually fast ones in a row? Or is there an unrecognized mechanism at work? One possibility involves galactic dynamics. The thick disk population, where Atlas appears to originate, consists of stars moving at different velocities relative to the Sun. If the object was born in that older population, its unusual speed might reflect differences in galactic motion, rather than unusual ejection conditions. But even this explanation raises unease. If Atlas has wandered since the Milky Way's youth, it has survived epochs when stars were more violent, collisions more common, and radiation more intense. How has it endured? The faster it moves, the less time for decay, but billions of years remain billions of years. Its persistence feels unreasonable. From a purely practical standpoint, ATLAS's speed means no spacecraft we possess can catch it. Even if we launched at Discovery, the delta V required to intercept exceeds the capabilities of any current propulsion system. By the time a mission could be designed, tested and launched, the visitor would already be gone. This asymmetry underscores humanity's helplessness when confronted with interstellar mysteries. We observe, we speculate, but we cannot interact. Speed protects the object from us, just as effectively as distance or disguise. The numbers themselves carry a certain weight. At 130,000 miles per hour relative to the Sun, Atlas crosses the continental United States in less than 3 minutes. In the time it takes to read this sentence, it has travelled tens of kilometres. Its hyperbolic excess speed of 61 kilometres per second ensures that not even the Sun can slow it down enough to remain. Gravity curves its path but cannot bind it. We are left with a brief glimpse, a cosmic flyby too fast for comfort. Yet speculation thrives in such environments. What if the velocity profile is not purely gravitational? What if Atlas is shedding mass in ways that mimic cometary activity, but are tuned to maintain or alter velocity with purpose? Outgassing produces non-gravitational accelerations, and comets frequently deviate from purely gravitational predictions. But those deviations are chaotic, tied to heating, rotation, and sublimation. If Atlas shows systematic deviations instead, subtle but measurable, it could suggest propulsion masquerading as natural processes. Current data shows no such anomalies, but detection thresholds matter. The difference between natural outgassing and controlled thrust might be invisible at interstellar scales. There is also the psychological effect of such speed. Humans are instinctively uneasy with uncontrolled fast-moving objects, especially when they come from beyond. We measure threats not only in terms of impact probability, but in terms of unpredictability. An object moving this fast, immune to capture, indifferent to our attempts at interception, feels threatening even when it poses no collision risk. It triggers a primal response. Something powerful has entered our domain, something beyond our control. The official reassurances from NASA and ESA emphasize safety and scientific value, but beneath the calm language lies an unspoken truth. Our helplessness is absolute. If Atlas were to change course, we could do nothing. If it were to deploy smaller objects, we could not stop it. If it were simply to continue on its way, we would remain as spectators, powerless to affect its passage. Its speed is not just a number, it is a barrier separating us from agency. We watch because watching is all we can do. This recognition shapes the worst-case scenarios. The most frightening aspect of ATLAS may not be what it is, but how quickly it moves. The pace of its journey robs us of time to prepare, to analyse, to respond. If it were an emissary, we would have only months of data before it vanishes. If it carried hidden systems, they could activate and deactivate before we ever noticed. Its speed ensures control lies elsewhere, not with us. For a species accustomed to studying the sky with patience and precision, this feels deeply unnatural. The cosmos usually unfolds slowly. Stars evolve over millions of years. Planets orbit in predictable rhythms. But Atlas does not wait. It races through, demanding urgency from creatures unaccustomed to such haste. We must accept that speed is part of the mystery. Whether natural or artificial, coincidental or designed, it defines everything about our interaction with this visitor. It is why we cannot intercept, why we cannot contain, why we cannot confirm or deny speculative scenarios with certainty. It guarantees the event is temporary and irreversible. By the time humanity reaches technological maturity capable of intercepting such objects, ATLAS will be gone, carrying its secrets into interstellar night. We are left only with data, fragments of spectra, images of a faint coma, orbital elements plotted on charts, all of it filtered through the distortion of speed. The visitor that should not exist moves with speed beyond reason, and that speed ensures our ignorance. It leaves us in the uncomfortable position of wondering whether our instruments capture truth or illusion. Perhaps it is only a comet, accelerated by cosmic chance. Perhaps it is more. We cannot know. What we do know is that it moves too quickly for answers, and as it races toward perihelion, our time to question dwindles as surely as its distance to the sun. From the earliest images of 3I/ATLAS, scientists encountered a familiar challenge. When dealing with comets and interstellar objects, size is never straightforward. Unlike solid asteroids, whose shapes can often be measured directly from reflected light curves, comets veil themselves in comas, diffuse clouds of gas and dust that expand thousands of kilometers beyond their nuclei. The result is a kind of astronomical disguise. The glowing envelope reveals activity but conceals the actual body beneath. With a TLAS, that disguise has become especially effective. The range of estimates places its core anywhere from a few hundred meters to more than 5 kilometers across. Such uncertainty is more than a minor inconvenience. It is the difference between a large boulder and a small mountain, between something fragile enough to shatter in interstellar space, and something robust enough to endure billions of years of wandering. The size problem, therefore, is not just about measurement. It is about survival, probability, and the unsettling possibility that the very uncertainty itself conceals something intentional. Determining the size of distant objects requires assumptions. Scientists measure the brightness of the coma, subtract estimated contributions of dust and gas, and apply models of albedo, the reflectivity of the underlying surface. A darker surface yields a larger nucleus for the same observed brightness, while a highly reflective surface implies something smaller, but Atlas complicates this process. Its unusual chemistry means its outgassing rates do not fit typical cometary templates. The carbon dioxide dominance identified by the James Webb Space Telescope suggests a composition far from ordinary, raising doubts about whether conventional comet models even apply. If the coma is brighter than expected because CO2 is venting more efficiently than water, then the nucleus could be much smaller than current estimates. If, however, the coma is hiding a much larger core insulated by processed crust, then our numbers may underestimate. Either scenario leaves us grasping for certainty that refuses to arrive. Smaller objects should not survive interstellar journeys lasting billions of years. A nucleus just a few hundred meters across would be vulnerable to tidal disruption during ejection from its natal star system. It would be more easily fractured by collisions with dust grains, each impact delivering tremendous energy at relative velocities of tens of kilometers per second. Over eons, even the sparse interstellar medium should wear away such a small traveller. Radiation exposure would strip volatiles, leaving only inert rock drifting dark and lifeless. And yet Atlas shows activity, gas venting into space in quantities large enough to be detected across astronomical units. If the nucleus is truly small, then survival itself becomes inexplicable. Something must have protected it, or something must have renewed it. Either explanation strains our naturalistic assumptions. A larger nucleus, perhaps several kilometers across, solves the survival problem but creates another. Larger bodies ejected from their systems are much rarer. The mechanics of gravitational slingshots tend to expel smaller debris more easily. A massive body has more inertia, requiring more powerful encounters to hurl it into interstellar space. The fact that ATLAS might be both large and ancient challenges statistical expectations. Did we stumble upon an unlikely survivor by pure chance, or are we observing something designed to be larger than necessary precisely to endure? If it is indeed a probe camouflaged as a comet, a larger size provides storage for systems, shielding for delicate instruments, and redundancy against cosmic attrition. The size problem begins to feel less like a measurement challenge and more like a potential clue. There is another aspect of this puzzle. Brightness varies as comets rotate. By charting fluctuations in light curves, astronomers can estimate rotational periods and infer shape. But Atlas's brightness has remained stubbornly uniform, at least so far. This consistency complicates rotational models. Either it rotates in a way that produces nearly symmetrical light output, or the coma is masking variations. If it is small, we should expect more dramatic shifts as different surfaces sublimate. If it is large, rotation should still leave subtle signatures. The fact that we see neither raises the suspicion that we are missing something. A probe designed to mimic cometary behaviour would need to manage its light output carefully, ensuring apparent randomness while concealing deliberate changes. Atlas's oddly stable brightness may be nothing more than natural coincidence, but it also fits too neatly with the requirements of effective disguise. The question of size ties directly into survivability across time. A nucleus just half a kilometre wide should not carry enough volatile material to remain active after billions of years. Even a larger one faces difficulties. Sublimation depletes reserves. Cosmic rays alter chemical structures. Impacts fracture surfaces. How then does ATLAS arrive not only intact but still active? Some scientists propose that insulating dust layers may have sealed inner reservoirs, preserving volatile stores until solar heating released them. Others suggest that cosmic radiation may have modified its chemistry, producing layers that delayed sublimation until now. These explanations, while plausible, feel more like excuses than answers. They patch holes in our understanding rather than explain why this particular object continues to defy expectations. The speculative alternative is more disturbing. If Atlas is not merely a random interstellar rock but something constructed, its size becomes purposeful. Large enough to endure, small enough to remain inconspicuous, capable of carrying both disguise and payload. In such a scenario, the coma is not a natural outgassing cloud, but a managed exhaust, designed to mimic cometary signatures while concealing systems within. The uncertainty in our measurements then becomes not an accident, but the result of deliberate engineering. By ensuring that any calculation of its true size remains ambiguous, such a craft would maximize its ability to pass as natural. We find ourselves measuring exactly what it wants us to measure. Astronomers are reluctant to wander down these speculative paths, yet the size problem forces the question. Even when sticking to natural explanations, the object does not behave like anything else we have studied. Oumuamua was long and thin, tumbling erratically. Borisov looked more like a standard comet but showed chemistry that puzzled researchers. Atlas continues the trend of anomalies, each new interstellar visitor straining the boundaries of our models. How many times can we encounter anomalies before anomalies themselves become the norm? Another difficulty lies in comparisons. Within our own solar system, comets range widely in size, from a few hundred meters to tens of kilometers. Their activity varies accordingly, with larger ones sustaining tails across months while smaller ones sometimes disintegrate in a single close pass. Yet Atlas, with its ambiguous size, seems to maintain a level of activity inconsistent with either extreme. If it is small, its activity is too vigorous. If it is large, its coma is too faint. It inhabits a statistical no man's land where neither small comet nor large comet explanations feel adequate. The numbers resist coherence, leaving open the uncomfortable possibility that our categories themselves are inadequate. For planetary defense researchers, size estimation is more than an academic exercise. An object 1 kilometer wide could cause planetary scale damage in the unlikely event of collision. An object only a few hundred meters across could devastate a region but not an entire world. NASA and EA calculate impact probabilities carefully, even when trajectories clearly show no threat. With Atlas, the numbers matter less for hazard assessment and more for understanding what this visitor truly is. But the inability to pin those numbers down illustrates our limitations. Even with the most advanced telescopes in history, we are left guessing whether this ancient traveller is mountain-sized or boulder-sized. The very ambiguity becomes part of the mystery. The role of size in worst-case scenarios cannot be overstated. If Atlas is small yet remains intact after billions of years, then our understanding of survival in interstellar space must be rewritten. That alone would challenge astrophysics at a fundamental level. If it is large, then its very presence near our solar system becomes improbable to the point of discomfort. And if the uncertainty is itself evidence of concealment, then we may be facing not just a scientific puzzle, but an existential one. Which outcome is worse? Realizing we know far less about cosmic survival than we thought, or realizing that survival was never natural in the first place? When scientists publish their estimates, they do so cautiously, attaching ranges and uncertainties, leaving space for revision. But the public craves certainty, and the media amplifies whichever number sounds most dramatic. The truth is less satisfying. We simply do not know how big ATLAS is. That ignorance forces us to confront not only gaps in our measurement techniques, but the possibility that some mysteries are designed to remain unsolved. The worst-case scenario is not impact, not collision, but ambiguity itself, a permanent uncertainty about whether we have glimpsed a relic of cosmic history, or the product of intelligence so advanced that it hides its scale behind the glow of its coma. The size problem, then, is not a technical footnote, but a central theme in understanding this visitor. It leaves us questioning the survival of small bodies, the improbability of large ones, and the unsettling possibility that uncertainty itself is the message. Atlas refuses to reveal its true dimensions, and in that refusal lies the real mystery. As it continues its journey toward perihelion, the coma will grow brighter, the nucleus more obscured, the estimates no closer to agreement. We watch, we calculate, and we speculate, but the core remains hidden. Perhaps that is exactly how it was meant to be. When we call 3I/ATLAS an interstellar object, we mean more than a visitor from another star. We mean a survivor. The galaxy is not gentle. It is a place where collisions, gravitational tides, radiation storms and cosmic catastrophes rule over billions of years. Most small bodies never last long enough to tell their stories. They shatter, scatter, or evaporate in the heat of stars and the violence of encounters. Yet Atlas arrives intact, still carrying volatiles, still showing activity, as if it has defied every destructive force the Milky Way has hurled at it for eons. The very fact of its arrival demands explanation, because survival in a galaxy this hostile is never guaranteed. The thick disk origin suspected for ATLAS makes the puzzle sharper. That population of stars is old, dating back 10 to 12 billion years, when the Milky Way was younger, more chaotic, and more violent. Star formation then was turbulent, heavy with collisions, mergers, and intense radiation fields. If Atlas truly comes from that population, it has endured conditions no solar system body we know has ever faced. It would mean the object predates Earth, the Sun, and every planet we orbit. It would mean it has been travelling longer than complex life has existed on our world. For something that old to remain coherent, still ejecting gas, still bright enough to track with telescopes, strains the limits of what natural survival should allow. Consider what an interstellar journey involves. The space between stars is not empty. Dust grains and stray atoms lurk in every cubic centimetre. At the speeds Atlas travels, colliding with even a microscopic particle is like enduring a constant barrage of bullets. Over millions of years, such collisions erode surfaces, chip away at structures, and gradually grind objects down. Over billions of years, erosion should be severe enough to reduce small comets to rubble. Radiation compounds the problem. Cosmic rays, high-energy particles streaming through the galaxy, strike surfaces relentlessly, splitting molecules, altering chemistry, and building crusts of altered material that seal away volatiles. For an object to remain active after such exposure, it must either be unusually large, unusually robust, or protected in ways we do not understand. Natural explanations exist, though each comes with limitations. One is that Atlas formed with an unusually thick reservoir of volatiles, deep layers of carbon dioxide and water ice buried beneath protective crusts. Over time, radiation may have sealed the surface further, delaying outgassing until solar heating penetrated fresh layers. Another possibility is that Atlas spent much of its journey in relatively quiet regions of interstellar space, away from high-density dust lanes or supernova blast zones. But even the quietest regions are not safe for billions of years. Survival begins to look less like probability and more like an anomaly. Speculation grows naturally from anomalies. If survival seems too unlikely, then perhaps survival was ensured. Perhaps Atlas is not merely a piece of debris, but a construct designed to endure interstellar voyages. If so, its persistence across galactic time is not coincidence, but purpose. Its crust might be armour, not accident. Its chemical reservoirs might be fuel, not fossils. Its activity might be engineered to mimic natural sublimation, ensuring that when discovered, it blends seamlessly into expectations. A device camouflaged as a comet could survive indefinitely if built with durability in mind. Its resilience would be the first and most convincing feature of its design. Even without invoking engineering, the implications of survival are profound. If comets like Atlas routinely cross the galaxy, then planetary systems everywhere are interconnected by material exchange. That exchange means chemistry from ancient stars reaches young systems like ours. It means that the building blocks of planets and life may not be confined to their birthplaces. Panspermia theories thrive in such contexts, suggesting that life itself may ride aboard such survivors, enduring across millions of years until deposited in welcoming environments. Whether natural or artificial, survival across the violent galaxy carries consequences for our understanding of origins. The violence of the galaxy is not limited to dust and radiation. Gravitational encounters represent another major threat. As interstellar objects wander, they pass near stars, planets, and even black holes. Each encounter can alter trajectory, accelerate speed, or tear an object apart. The fact that ATLAS remains whole implies either extraordinary luck or extraordinary resilience. A small, fragile body should not withstand close encounters without fracturing. A robustly constructed one might. Again, the line between improbability and intention blurs. How many close encounters has ATLAS survived? How many stellar flybys? How many times has it passed through the outskirts of planetary systems, each encounter a chance for capture, collision, or destruction? Its continued presence suggests a resilience that exceeds expectations. The worst-case scenario here is not that Atlas threatens Earth directly. Its trajectory remains safely distant. The worst case is that its survival signals a truth we are not ready to confront, that the galaxy is filled with such wanderers, carrying not only chemistry but possibly information, technology, or even life. If they are all natural, then survival is less improbable than we thought, and the galaxy is more connected than we imagined. If they are not natural, then survival is evidence of design, and the galaxy is less empty than we hoped. Either way, our assumptions about isolation and uniqueness begin to crumble. Astronomers sometimes compare interstellar objects to messages in bottles. Cast adrift from their home systems, they wander indefinitely, carrying within them chemical records of distant times and places. But Atlas may be more than a bottle. It may be a vault, built to withstand the chaos of a violent galaxy, carrying not just random messages but curated ones. What might such a vault contain? Sensors gathering data? Instruments waiting for activation? Encoded chemistry designed to reveal itself under certain conditions? If so, then the true worst-case scenario is not collision but revelation. That when Atlas survives the violence of the galaxy, it does so because it was always meant to reach us. Even if we set aside such speculation, the natural survival of ATLAS is still unsettling. If objects can endure for billions of years, then the galaxy may be filled with them, crossing every system, carrying foreign chemistry everywhere. That implies a constant mixing of matter across the galaxy, a quiet but relentless exchange that makes every system less isolated. It means that Earth's chemistry, perhaps even life's precursors, may already be scattered across other stars, just as theirs may be scattered here. The Milky Way becomes less a collection of separate worlds, and more a single ecosystem linked by survivors like Atlas. Survival, in this sense, is not just improbable, it is transformative. The violence of the galaxy should have erased Atlas long ago. That it remains forces us to question whether our models of destruction are too pessimistic, or whether our assumptions about natural survival are incomplete. Perhaps we underestimate the ability of small bodies to endure. Perhaps our sample size of one solar system misleads us, or perhaps we are witnessing something entirely different. Either way, ATLAS stands as a contradiction. A survivor where none should exist, a traveller older than our world, carrying within it secrets from a galaxy too violent to allow them. The size problem and the speed anomaly were troubling enough, but survival magnifies them. Together they suggest not accident, not randomness, but pattern. And pattern is where worst-case scenarios begin. When astronomers first pointed the James Webb Space Telescope at 3/ATLAS, expectations were modest. Perhaps it would show a chemical profile broadly similar to Borisov, the second interstellar visitor, or echo the strange outgassing patterns that had puzzled researchers with Oumuamua. Instead, the data came back with something more puzzling. The spectrum revealed an object dominated by carbon dioxide, outgassing in proportions unlike anything seen in solar system comets. The ratios of carbon dioxide to water, carbon dioxide to other volatiles, stood far outside the norms established from decades of cometary study. The numbers were not simply unusual, they were alien in a way that challenged models built on our own local sample of cometary bodies. In our solar system, comets are time capsules of the early planetary disk. They usually carry water ice, carbon monoxide, carbon dioxide, methane, and other volatiles in varying proportions. The dominant signature, however, is almost always water. Even when carbon dioxide is present, it tends to be secondary, a supporting component rather than the main driver of activity. With ATLAS, the script flipped. Water seemed strangely absent or at least suppressed, while carbon dioxide was elevated to levels that defied easy explanation. A chemistry out of place, inconsistent with the environments we know, implied formation under conditions vastly different from our own. If Atlas formed in a region of its natal disk where temperatures were colder than anything in our solar system, carbon dioxide could have frozen in abundance while water remained sequestered deeper. Alternatively, if it formed closer to its star, high heat might have depleted water before the body was ejected. Either scenario strains conventional planetary models. For decades, astronomers assumed interstellar comets would resemble our own, because planetary formation follows universal laws of physics. The surprise is that laws do not always yield the same results. Chemistry diverges, ratios shift, and in those shifts lies the possibility of discovering processes we had never considered. The carbon dioxide dominance was not the only anomaly. Spectral lines suggested additional features that did not fit well into templates. Subtle hints of complex hydrocarbons appeared, though their certainty remains debated. Dust signatures also differed, showing grain distributions unlike typical solar system comets. These deviations matter because they hint at environments our models do not capture. Perhaps Atlas formed in a system rich in carbon chemistry, poor in oxygen-bearing volatiles, and shaped by stellar radiation that never existed around our sun. That alone would make it valuable, a messenger carrying evidence of planetary conditions foreign to us. But speculation does not stop at natural formation. When chemistry appears out of place, the mind inevitably drifts toward design. What if the ratios are not natural outcomes but deliberate features? If a civilization engineered a probe to mimic a comet, it might choose volatiles that obscure detection. A coma rich in carbon dioxide produces spectral profiles that astronomers can explain away as unusual but natural. It creates just enough anomaly to spark scientific papers while remaining within plausible boundaries. Water, the most common cometary driver, is conspicuously faint here. That faintness might itself be a form of camouflage. A body venting water in typical patterns would be compared to known comets. A body venting something stranger would remain an anomaly, never quite natural but never conclusively artificial. Suspicion lingers without resolution. Carbon dioxide also carries practical advantages. Unlike water, it sublimates at lower temperatures, meaning activity begins farther from the sun. For a natural comet, this is a curiosity. For a disguised probe, it is a strategic choice. Early outgassing creates a veil, a shroud of dust and gas that obscures the nucleus before it ever reaches the inner solar system. Instruments attempting to measure the core's shape or rotation are hindered, forced to infer rather than directly observe. A cloud of CO2 provides both cover and consistency. The very chemistry that looks unusual might also serve as protection. Some researchers propose that ATLAS's chemistry reflects processing during its long interstellar journey. Cosmic rays could alter molecules, splitting water, enriching carbon dioxide in relative terms, and driving chemistry toward unusual ratios. Over billions of years, Surfaces exposed to radiation accumulate crusts rich in carbon-bearing residues. But again, the survival question reappears. Why does Atlas show abundant gas now if its volatiles were long ago stripped or altered? Radiation should have reduced activity, not prepared it for renewed vigour. Natural explanations feel like patchwork. They answer one puzzle while creating another. The deeper implication is that chemistry records history. If Atlas is natural, then its strange chemistry tells us of a planetary system radically unlike our own. If it is artificial, then its chemistry tells us of choices made by designers who wanted it to appear natural, yet different enough to avoid detection. Either way, the out-of-place chemistry is a signal, whether of environment or of intent. The challenge is deciding which. The role of carbon dioxide also intersects with discussions of habitability. On Earth, CO2 is central to climate, photosynthesis, and the cycle of life. In planetary atmospheres, it can regulate temperature, trap heat, and drive surface processes. A comet rich in CO2 but lacking water could in principle deliver massive amounts of the gas to a young planet, altering its climate trajectory. If many interstellar comets share this profile, then their role in seeding planetary systems could be profound. Instead of bringing water, they may bring greenhouse gases, reshaping early environments in ways we have not yet modelled. Such chemistry out of place could mean life elsewhere began under conditions unlike anything we consider habitable. But again, the darker speculation emerges. If a probe were to sample planetary atmospheres, measure greenhouse gas concentrations, or test climate responses, it might carry its own stores of carbon dioxide for calibration. Outgassing that gas would then appear to us as natural sublimation. The coma becomes both cover and instrument, blending science with disguise. The question is unsettling not because we have evidence, but because the chemistry itself fits both narratives too well. It can be explained as unusual natural formation or as deliberate camouflage. Neither answer resolves the ambiguity. The media often simplifies such discoveries. Headlines proclaim alien comet or cosmic oddity, reducing complex chemical analysis to sound bites. The truth is quieter and more unsettling. The numbers do not fit. The ratios are wrong. And in science, when ratios are wrong, it usually means either our models are incomplete or our assumptions are flawed. With Atlas, both may be true. Our models of cometary formation assume environments too similar to our own, and our assumptions about interstellar objects assume randomness, where perhaps patterns exist. Chemistry out of place is more than anomaly, it is contradiction. Contradictions demand resolution, but Atlas moves too quickly for answers. The worst-case scenario is not that the chemistry indicates life or intelligence. The worst case is that it indicates deception. If what we see is what it was designed for us to see, then every line of its spectrum is part of a mask. Every deviation from norms is camouflage, leading us down paths of natural speculation while concealing intention. The possibility that the object is not only out of place but deliberately so raises the stakes beyond curiosity. It forces us to ask whether we are being misled, and if so, to what end. Yet even the natural explanations remain disturbing. If Atlas is natural and its chemistry is representative of other systems, then our own solar system may be the outlier. Perhaps water-dominated comets are not the galactic norm. Perhaps elsewhere, CO2 rules, and water is scarce. That would reshape theories of habitability, planetary climate, and the distribution of life. Life as we know it may be rare not because conditions for water are rare, but because conditions for CO2 are common. If so, then chemistry out of place is not anomaly at all. It is a revelation that we are the unusual ones. As Atlas recedes from the sun, its activity will fade, its coma will thin, and its chemistry will vanish from our instruments. What remains will be papers, spectra, and lingering doubts. The ratios we measured will never change, but our interpretations will evolve. Future interstellar visitors may confirm or contradict these findings. Until then, we are left with a puzzle unresolved. A comet that looks natural but feels alien, whose gases whisper of environments we do not know, or of intentions we cannot confirm. The chemistry is out of place, and in that displacement lies the true mystery. Whether natural relic or disguised emissary, Atlas refuses to fit comfortably into our categories. It resists explanation, and in that resistance, it unsettles. When Oumuamua passed through the solar system in 2017, one of the first responses from astronomers was not optical or chemical, but radio. If the object were artificial, perhaps it would emit signals, transmissions, or coherent bursts in wavelengths associated with communication. Radio telescopes across the world turned their dishes toward it. They listened, patiently and carefully, for days and weeks, scanning a wide range of frequencies for anything that could not be explained by natural background noise. Nothing came, the silence was absolute. With 2I/Borisov the same protocol repeated. Dishes listened again, searching for patterns, narrowband signals, or anomalies. Again, silence. Now with 3I/ATLAS, the tradition continued. Massive receivers pointed at the visitor, listening across billions of channels. The results were the same. The object was silent, at least to ears tuned like ours. For many, silence is reassurance. It suggests that these objects are not machines broadcasting messages. It supports the conservative view that they are only comets, fragments of cosmic debris wandering without intent. Yet silence itself can also be unsettling. If one were to design a probe to move unnoticed among civilizations, silence would be its first defense. Emissions are detectable across light years. A careless transmitter gives away position and purpose. In a galaxy where survival might depend on secrecy, as some speculative models of advanced civilizations propose, the most effective communication strategy is none at all. Silence becomes not the absence of intent, but the clearest sign of it. In radio astronomy, detection relies on contrast. Natural sources produce broad, noisy emissions, pulsars, quasars, thermal radiation from dust and gas. Artificial transmitters, by contrast, tend to be narrowband, concentrated on a single frequency, carrying coherence not found in nature. That difference is why SETI researchers often describe narrowband signals as the smoking gun of extraterrestrial technology. But the absence of such signals does not mean absence of technology. It only means absence of communication that resembles ours. An advanced probe could operate on bands we cannot monitor, frequencies drowned by cosmic background, or modalities of transmission we do not yet understand. It could use spread spectrum techniques, distributing signals so widely that they appear as noise. To us, silence. To those who know the key, communication. The other problem is time. A transmission might not be constant. It might be intermittent, triggered by conditions we do not know. If Atlas is artificial, perhaps its radio silence is temporary, a waiting state until it reaches a particular alignment or receives a signal from elsewhere. We observed Oumuamua for weeks, Borisov for months, Atlas for its brief window, but in cosmic terms these are flickers. If activity occurs outside our listening period, we would never know. Silence is as much a product of our limited observation as of the object itself. The practical challenges are enormous. Radio telescopes cannot listen everywhere, at every frequency, all the time. They must choose. They point at certain objects, survey certain bands, and trade breadth for depth. Even when directed at ATLAS, they cover slices of spectrum. The odds of matching the right frequency, at the right time, with the right sensitivity, are slim. If Atlas does transmit, it may simply be that we were listening in the wrong way. Silence, then, is not evidence of nothing, but of mismatch. The absence of detection says more about us than about it. Yet there is something haunting in that mismatch. We expect nature to be noisy, Comets produce radio emissions through interactions of solar wind with their comas. Dust grains scatter electromagnetic radiation. Molecules in the gas emit at characteristic frequencies. When astronomers tuned in to ATLAS, they did detect natural emissions, lines associated with carbon dioxide, traces of other volatiles, but nothing coherent, nothing structured. The silence was not total, but it was natural silence. A background hum of chemistry, not the sharp voice of intelligence. We interpret that as safety. But again, if concealment is the goal, that is exactly what we should expect to hear. There is a paradox here. The more convincingly silent Atlas appears, the more effective it would be as a disguised probe. If we dismiss suspicion solely because our instruments hear nothing unnatural, then we hand victory to any intelligence capable of mimicking nature perfectly. The silence that reassures is also the silence that blinds. The worst-case scenario is not that Atlas is shouting and we fail to hear it. The worst case is that it is whispering in ways we cannot decode, or simply observing without need for transmission, and we interpret that as absence. Astronomers confront this paradox with cautious optimism. They remind us that natural explanations always fit silence better than artificial ones. Most objects in space do not transmit. They do not need to. The absence of signals is expected, but in this case, expectation itself becomes dangerous. We expected water to dominate cometary chemistry, and ATLAS showed carbon dioxide instead. We expected interstellar visitors to be rare, and 3 have arrived within a decade. We expected survival to be unlikely, and yet this one endures. At what point do expectations stop protecting us and start misleading us? In discussions of extraterrestrial intelligence, silence has another meaning. The Fermi paradox, the apparent contradiction between the high probability of life and the lack of evidence for it, has sometimes been explained as the result of deliberate quiet. Civilizations, fearing predation, hide themselves. They avoid transmission. They mask their signatures. They choose silence as survival. Atlas, if artificial, would fit into this model perfectly. A quiet probe, indistinguishable from debris, drifting past civilizations without revealing the presence of its makers. In such a framework, silence is not failure, but strategy. The galaxy could be filled with watchers, all quiet, all camouflaged, all avoiding detection by playing the role of comets and asteroids. The unsettling thought is that we may already have been observed, not once, not just by Atlas, but repeatedly, by countless silent watchers that passed unnoticed before we had the instruments to detect them. If the galaxy truly operates under rules of concealment, then ATLAS is not anomaly but confirmation. Its silence is the sound of a strategy far older and more effective than our brief attempts to listen. The worst-case scenario, then, is not that ATLAS is unique, but that it is typical. That silence in the radio spectrum is the universal language of intelligence in a dangerous galaxy. And so we listen, knowing that silence tells us little. The absence of a voice does not mean the absence of a presence. It only means that if the voice exists, it is not meant for us. As Atlas continues its swift arc through the inner solar system, radio dishes will continue to track it. Each day will bring data, confirming natural emissions, denying coherent signals. The reports will conclude that it is silent, another comet with nothing unusual beyond its chemistry and speed. Yet beneath those conclusions lies unease, because silence can mean 2 things, and we do not know which. It can mean natural. It can mean deliberate. Both interpretations remain open, and both carry consequences we're not prepared to face. Atlas drifts past, silent in our ears, loud in our thoughts. We can only wonder which silence we're hearing. When an object like 3I/ATLAS enters the solar system, the natural impulse is to classify it within familiar categories. Is it a comet? Is it an asteroid? Is it some hybrid of the two? Our models of small bodies are built on centuries of observation, and anything new is usually squeezed into existing definitions. But with each interstellar visitor, those definitions strain. Oumuamua looked like no asteroid or comet we had ever seen. Borisov resembled a comet, but with a chemistry that didn't match our own. Atlas arrived, showing even more contradictions, as if playing a role too convincingly. The natural explanations stumble one after another, and what begins as a search for classification slowly becomes something else. We start asking whether the object is not trying to fit into categories, but to exploit them. That question gives rise to what some call the disguise hypothesis. The disguise hypothesis suggests that ATLAS is not natural debris, but an engineered construct designed to appear natural. To us it looks like a comet, outgassing as sunlight warms its surface, cloaking itself in dust and gas. To us it travels on a hyperbolic trajectory consistent with ejection from another system. To us it shows nothing in radio, nothing in thermal, nothing to distinguish it from a random piece of frozen rock. But those are precisely the features a disguised probe would need. The disguise hypothesis takes silence, ambiguity, and anomaly not as signs of randomness, but as features of intent. Camouflage is a universal strategy in nature. On Earth, countless species survive by appearing as something they are not. Insects mimic leaves, fish vanish against coral, predators blend into their environments. If evolution converges on camouflage as a survival tool in a single biosphere, why would technology not converge on the same solution in a galaxy filled with unknowns? A disguised probe avoids detection, avoids interception, and avoids panic. It gathers information while its observers dismiss it as background noise. If humanity were to send probes into other systems, we too might consider disguise. Not because we plan harm, but because we would not want to trigger defensive responses from unknown civilizations. Disguise is not aggression, it is insurance. For Atlas, the disguise is layered. Its chemistry is unusual but not impossible. Its speed is extreme but not inexplicable. Its size is uncertain but within plausible ranges. Every feature pushes against boundaries but never fully breaks them. It is as if each anomaly were calibrated to raise questions without providing answers. Too many coincidences accumulate. We begin to wonder whether ambiguity itself is the disguise. A truly alien object would either scream its difference or hide it. Atlas does neither. It hovers between, forcing us to argue endlessly over natural versus artificial, never resolving, always doubting. That middle ground is the perfect camouflage. If the disguise hypothesis holds, then activity becomes suspicious. Cometary outgassing is unpredictable, dependent on heat, rotation, and volatile layers. But if a probe were venting gases deliberately, it could simulate those patterns convincingly. Controlled exhaust could mimic sublimation while adjusting trajectory, altering speed, or powering instruments. The veil of gas becomes not only cover but function. Observers like us see a coma and tail, we assume sublimation, and we stop asking questions. Behind the veil, systems operate freely. Our instruments are blinded not by distance, but by the very phenomenon we expect. The disguise is perfect because it uses our expectations against us. The most disquieting element of this hypothesis is its simplicity. Nothing about Atlas needs to be extraordinary to succeed as a disguise. It only needs to fit within the edge cases of natural behaviour. That is what makes it different from science fiction portrayals of alien probes. Those often feature impossible materials, glowing energy signatures, or obvious signs of intelligence. A real probe, if one existed, would do none of those things. It would be quiet, unremarkable, forgettable. The disguise hypothesis is not about spectacle. It is about invisibility. Skeptics push back, and rightly so. They argue that invoking disguise without evidence is a trap. Every anomaly in astronomy can be explained by pushing models farther. We did not know comets could contain such ratios of volatiles, but now we do. We did not expect interstellar visitors to be so frequent. but perhaps our models underestimated their density. They warn against filling gaps with intention when nature has repeatedly surprised us with phenomena stranger than fiction. That caution is well placed. But the disguise hypothesis does not require proof. It only requires possibility, and in worst-case scenarios, possibility is enough. If Atlas is disguised, the next question is purpose. Why here? Why now? A probe crossing the solar system could gather immense data simply by passive observation. It could measure radio leakage from Earth, monitor satellite traffic, map magnetic fields, and analyze atmospheric chemistry. All of this can be done silently without interaction. Disguise ensures we do not notice, or at least that we dismiss what we notice. Even if we suspect, as some do, that it might be artificial, our official response remains cautious. We treat it as natural because that is safer. Disguise works not by hiding completely, but by making us complicit in denial. This complicity matters. Humanity's reaction to Oumuamua was fascination but not fear. To Borisov, curiosity but not alarm. To Atlas, again interest but no crisis. If each was disguised, then the strategy works flawlessly. The visitors come and go, we measure and debate, we publish papers and move on. The cycle repeats, each time leaving us with data but no certainty. Meanwhile, if the probes are real, they accumulate knowledge across countless civilizations, unnoticed and unchallenged. Disguise does not just protect the probe, it protects the mission. The disguise hypothesis also forces us to reconsider our definitions of evidence. In science, extraordinary claims require extraordinary proof. But in intelligence analysis, extraordinary absence can itself be suspicious. If an object moves like a comet, looks like a comet, and outgasses like a comet, but every detail of its behaviour pushes exactly against the edges of cometary expectations, the pattern itself becomes suspicious. Too many coincidences stop being coincidences. The disguise is not in the features, but in the way they align just so, convincing but never conclusive. This leads to a deeper fear. If Atlas is disguised, then our instruments may not be capable of unmasking it. The disguise may be perfect at our level of technology. Perhaps with better telescopes, with probes of our own, we might resolve the nucleus, measure emissions precisely, detect deviations in trajectory. But by then it will be gone, already receding into the void. We are always too late, too slow, too limited. The disguise does not need to fool us forever. It only needs to fool us long enough for the object to pass through unchallenged. That is a chilling thought, because it means we might have already missed dozens or hundreds of disguised visitors before we even realised they existed. There is no need to invoke malice here. A disguised probe does not have to mean invasion or threat. Observation is enough. But the worst-case scenario is not invasion. The worst case is that disguise itself is the universal strategy of advanced civilizations, and that we are surrounded by observers we will never detect. Atlas would then be not exception but example, proof of a galaxy filled with silence, camouflage, and watchers hidden in plain sight. If so, then our place in the universe is not isolated but surveyed, not unique but catalogued. That realization would change our understanding of existence more than any direct contact could. For now, the disguise hypothesis remains speculation. It has no direct evidence, only anomalies arranged in suggestive patterns. Astronomers prefer natural explanations and the data supports them. But the hypothesis lingers because it fits too well, because it explains too much, because it feels like the missing piece in a puzzle we cannot solve. Atlas passes, we measure, and we remain unsure. Disguise thrives on uncertainty, and uncertainty is all we have. When astronomers traced back the trajectory of 3I/ATLAS, the numbers pointed not to the thin disk of the Milky Way, where our Sun resides, but to the thick disk. The thick disk is an older, stranger neighbourhood of the galaxy. a population of stars that formed more than 10 billion years ago when the Milky Way was still assembling itself. These stars orbit differently, at steeper inclinations, moving faster relative to the Sun. They are older, dimmer, poorer in metals. To find an interstellar comet from this population is remarkable enough. To consider what it means if the object is something more than natural is even more unsettling. If Atlas is truly a product of the thick disk, then we are looking at something with origins far older than Earth itself, perhaps tied to civilizations that predate our planet by billions of years. The thick disk is a fossil of the galaxy's youth. Its stars tell stories of a time when supernovae were common, when galaxies collided and merged, when turbulence defined everything. Worlds around those stars would have formed under harsher conditions than ours, with lower metallicity, fewer heavy elements for building rocky planets, and greater exposure to radiation. The conventional wisdom is that such environments are less favourable for life. But if Atlas comes from there, then either comets formed and survived in that ancient chaos, or something else was at work. The very presence of the object challenges our assumptions about where survivability is possible. For astronomers, the orbit of ATLAS is a map. By projecting its velocity backward, they can trace its path into the galaxy, though uncertainties grow the further they go. Even with limited precision, the conclusion remains the same. The object is not part of the thin disk population. Its motion matches that of the thick disk. That means it is not just interstellar but intergenerational. A body older than our own solar system, travelling since before the Earth cooled from molten rock. It means that while life here has risen and fallen, while species have gone extinct and civilizations have risen, Atlas has been wandering, indifferent to all of it. This indifference is natural for debris. Rocks do not care. Ice does not watch. But if the object is not debris, then its origin becomes a matter of intent. A probe from the thick disk would not be merely old. It would be unimaginably old, designed by beings that lived and died before our world even existed. That possibility is difficult to imagine, not only because of the scale of time involved, but because of the challenge of persistence. What kind of technology could last 10 billion years? What kind of purpose could guide a mission that endures for spans longer than entire galaxies remain stable? These are not questions of science as we practice it, but of philosophy and speculation, yet they cannot be avoided when we speak of ATLS as a navigator of the thick disk. In one interpretation, ATLAS is natural, ejected from a star in the thick disk billions of years ago, surviving impossibly long to pass through our system now. That itself is extraordinary. In another darker interpretation, ATLAS is artificial, a probe designed not just to cross interstellar distances, but to traverse galactic epochs. In this view, its disguise as a comet is not for us specifically, but for anyone it encounters, anywhere, at any time. It has been navigating for billions of years, hidden in plain sight, moving among stars, appearing natural to every civilization it passes. If that is true, then we are not the first to see it, nor will we be the last. We are merely one more species in a line of countless others, all of whom noticed an odd comet, all of whom debated natural versus artificial, all of whom eventually let it pass into the night. The thick disk origin also suggests something about strategy. If a civilization from that population launched probes, they would understand that the galaxy is violent and unstable. They would design their machines to survive radiation, dust, collisions, and time itself. The design choices would be invisible to us, buried under the appearance of natural cometary crusts. But they would explain survival in environments that should have destroyed smaller, weaker objects. The navigator hypothesis fits too neatly. A body travelling impossibly long and impossibly far because it was built for that very purpose. The worst-case scenario is not that Atlas is from the thick disk. That much is almost certain. The worst case is that it is not travelling by accident but by intent. That it is not a random survivor but a navigator, a scout, part of a system of exploration so vast and so old that we cannot comprehend its scope. If such a system exists, then the galaxy we inhabit is already mapped, already observed, already catalogued by powers that passed their prime before our planet was born. Humanity would then not be explorers of the galaxy, but latecomers to a charted territory. This idea unsettles because it undermines one of our most cherished assumptions, that the galaxy is waiting for us, that we are early or rare or special. But if probes like Atlas are navigators of the thick disk, then we are not early and we are not special. We are one among many, observed long before we were aware. That realization reframes everything. Our telescopes, our search for life, our dreams of expansion, all take place within a galaxy where others have already walked, others have already sent watchers disguised as comets. We are not at the beginning of a story. We're entering in the middle without knowing who wrote the first chapters. Astronomers working on ATLAS emphasize natural models because that is their responsibility, but the disguise hypothesis and the navigator hypothesis persist outside the boundaries of formal papers. Among those who speculate, the thick disk origin is too striking to ignore. A body this old should not be here, and yet it is. Natural explanations falter. Artificial ones disturb. Neither feel satisfying, and so the ambiguity remains. The reality is that we may never know. Atlas will pass, leaving behind only data, debates, and doubts. But its trajectory into and out of the thick disk will remain. It forces us to confront the possibility that the galaxy is not just a stage for natural processes, but a network already traversed by machines older than we can imagine. If Atlas is navigator, then we are not alone, not because someone is watching us now, but because someone was watching long before we existed. The worst-case scenario is not threat, it is irrelevance. To realize we are part of a galaxy already mapped is to realize we are not discoverers but discoveries. And Atlas continues on, silent, disguised, unmeasurable in size, unreasonable in speed, its chemistry out of place, yet its trajectory clear. It came from the thick disk, and it will return to it. Whether as debris or as probe, it remains a survivor of galactic history, a traveller through time as much as through space. We can only watch, only speculate, only wonder if what passes before us is nature's relic or someone else's design. Every orbit tells a story. For natural bodies, that story is shaped by gravity alone. Rocks and ice obey Newton, and their motions are predictable, inevitable, the sum of forces acting upon them. When an interstellar object like 3I/ATLAS enters our system, astronomers plot its path with precision, measuring angles and velocities, mapping its hyperbolic escape. The mathematics is exacting, and in those numbers scientists find reassurance. It moves as expected, it follows physics, it does not deviate. But hidden inside that reassurance is an unease, because trajectories can also deceive. What looks natural can still be intentional. A path can mimic randomness while being chosen. A curve through space can look like chance while hiding design. At some point, trajectories stop looking accidental and start resembling intention. Oumuamua raised this question first. Its acceleration, too small to be explained by gravitational forces, sparked speculation. Some called it outgassing, some called it radiation pressure, others dared to suggest propulsion. The debate never settled. Borisov seemed more ordinary, its path explained by cometary activity. But then came ATLAS, arriving faster from older stellar populations, carrying anomalies in chemistry and structure. Its trajectory, plotted back into the galaxy, places it in a region filled with uncertainty. Its future path, hyperbolic and precise, guarantees escape. Both facts seem natural, but the pattern is troubling. When every interstellar object we detect carries unusual features, at what point do the anomalies accumulate into something more? The disguise hypothesis overlaps with this. A disguised probe would choose trajectories that appear natural. The easiest way to avoid suspicion is to obey orbital mechanics. If Atlas were artificial, its controllers, or its designers, if it operates autonomously, would ensure it never deviated in ways that revealed intent. It would ride a hyperbolic arc exactly as expected, never offering proof of control, but small deviations masked as outgassing could allow it to adjust course slightly, refining its flyby of targets. To us, the data would look like cometary physics. To them, it would be steering. There is precedent for this kind of deception in human history. Military aircraft fly routes that resemble civilian paths. Submarines trail thermal wakes that blend into ocean currents. Drones move like birds on radar. In each case, the trick is to hide intention beneath the expected. In space, intention is hidden by gravity. If Atlas is more than natural, then its trajectory is its camouflage. It moves exactly as we expect because it must. Anything else would expose it. And yet there are subtleties. Its inbound vector is unusual. Its velocity relative to the Sun is higher than typical models predict. Its origin in the thick disk is improbable. Each of these alone can be explained. Together they feel less like chance. The unsettling possibility is that what we see as coincidences are in fact choices. Atlas's trajectory may look random to us, but perhaps it was selected to pass near certain stars, certain systems, certain planets. Perhaps we are one of those stops. If so, then our perspective changes entirely. We're not watching a comet passing by. We're being visited by a traveller whose path was chosen long before we noticed it. Of course, scientists resist such thinking. They point out that selection bias colours everything. We detect only the visitors that happen to pass near Earth. Countless others go unseen, and the ones we notice will naturally seem unusual. That argument has weight, but it does not erase the question. Even if only a fraction are unusual, even if only some trajectories look intentional, then the possibility remains that among them are true navigators, not random wanderers. The fact that Atlas is only the third we have studied makes the anomalies stand out even more sharply. Trajectory also defines opportunity. The flyby geometry of a TLAS allows us to observe it, but never to reach it. Its speed ensures escape. Its path ensures brevity. This is convenient if it were a probe. A trajectory that passes close enough to study but far enough to avoid danger is exactly what a cautious mission planner would design. The object gathers information and then departs before the locals can interfere. To us it is natural, to them it is strategy. Again, the line between accident and intent blurs until they become indistinguishable. This ambiguity is the heart of the problem. We cannot distinguish between a natural trajectory and an intentional one if the intention is to appear natural. Orbital mechanics is the perfect disguise. It allows something artificial to hide indefinitely, moving through system after system, unchallenged, unquestioned, until one species learns enough to notice the oddities, but not enough to prove them. Humanity may now be at that stage, able to see anomalies, unable to resolve them. Atlas is the embodiment of this tension. We can measure its speed, its orbit, its escape, but we cannot know if those numbers are the whole truth. The worst-case scenario is not that ATLAS collides with Earth. Its path is far too distant. The worst case is that its trajectory is not a line of chance but a line of purpose, that it has passed by many civilizations before, each one debating the same questions, each one concluding naturalness because it was safer, each one catalogued as data. If Atlas is a disguised probe, then its trajectory is intentional in the most unsettling way. Not chosen for us, but chosen to pass through every possible system over billions of years. A slow survey of the galaxy disguised as random wandering. We would then not be the first to see it, nor the last. We would only be one more waypoint on a route written long ago. The human mind struggles with this kind of scale. We are used to thinking of missions that last years, decades at most. Voyager has been travelling for less than half a century. Our satellites last years before they fail. The idea of a machine travelling for billions of years, across galactic distances, on a trajectory that looks random but serves a plan, feels impossible. And yet, if civilizations older than ours existed in the thick disk, perhaps this is exactly what they achieved. Perhaps they mastered the art of hiding intent within gravity, embedding machines in paths that span galactic epochs. The trajectory becomes the mission, the disguise becomes the reality. Astronomers continue to track ATLAS, refining its orbit with every observation. The data confirms naturalness, but confirmation only measures what we expect. Small deviations could exist below our thresholds, adjustments too subtle to detect. We cannot rule them out. That inability is itself a problem. The silence in the radio spectrum, the chemistry out of place, the speed beyond reason, all combine with the trajectory to create a picture we cannot resolve. The numbers tell us it is a comet. The anomalies whisper it might not be. Between the two lies the disguise, and within the disguise lies intention. For now, ATLAS moves exactly as predicted. It follows its path without deviation. It reassures astronomers and unsettles speculators, but reassurance can be the most effective deception, and unsettling patterns the faintest hint of truth. We do not know which we are seeing. We only know that trajectories can look like intentions, and sometimes intentions look exactly like trajectories. When scientists first confirmed the existence of Oumuamua in 2017, the announcement carried a kind of wonder. After centuries of searching the skies, we had finally seen an object from beyond our solar system. Just 2 years later, Borisov arrived. Another interstellar visitor, this time unmistakably cometary, displaying a tail that left little doubt. And now, within the span of less than a decade, a third appears, 3I/ATLAS. The probabilities suggested by older models said these discoveries should be rare, once-in-a-century events, perhaps even rarer. Instead, 3 in less than 10 years. Timing like this forces questions. Are we simply lucky, or is luck the wrong word? Perhaps the coincidences are not coincidences at all. Cosmic timing is a slippery thing. The universe is vast, the scale of events incomprehensible. Stars live for billions of years. Galaxies collide over eons. Even comets within our own system can take thousands or millions of years to complete their orbits. Against that backdrop, the sudden arrival of 3 interstellar wanderers in quick succession seems improbable. Astronomers have tried to reconcile the numbers, suggesting that perhaps interstellar objects are far more common than once believed, that our models underestimated how often they pass through. That explanation is possible, but it also feels like a retreat. To fix the timing, we rewrite the probabilities, but rewriting does not erase the pattern. If these objects are natural, then their arrival in this window of human history is staggering coincidence. For hundreds of thousands of years, they must have slipped by unnoticed, invisible to naked eyes, ignored by cultures who could not track them. Only now, with telescopes capable of scanning the sky in real time, do we see them. The coincidence is timing not of the objects themselves, but of us. We exist in the narrow sliver of history when we can finally detect what has always been passing through. That explanation satisfies some, but it leaves others uneasy. Why now? Why 3? Why all with anomalies that strain natural categories? Speculation grows in the spaces where numbers refuse to settle. If the timing is not coincidence, then it may be design. If the objects are probes, then perhaps their arrival is not random but scheduled. If you were an advanced civilization monitoring young species across the galaxy, you might time your visits to coincide with technological emergence. You would not send probes during the Stone Age, when no one could detect them. You would not wait until civilizations mastered interstellar travel, when they might intercept. You would send them now, in the fragile moment when a species first gains telescopes, first develops radio, first learns to see. The perfect timing is the moment of awakening. That is when disguise is most effective, because curiosity explains anomalies while fear dismisses them. The cosmic timing becomes deliberate. The unsettling implication is that we are being observed not by accident but by schedule. The window of our detection aligns with the window of their intent. Each object, Oumuamua, Borisov, ATL, ASS, arrives to mark a stage in our development, each one different, each one designed to provoke curiosity without offering answers. A thin sliver of data, enough to spark debate, not enough to settle it. If this is design, then the intent is not communication but calibration. They measure how we respond, how quickly we turn from natural explanation to speculation, how willing we are to consider the possibility of disguise. The timing itself becomes the test. Skeptics remind us that the simplest explanation is observational bias. The telescopes that discovered these objects, the Pan-STAR system in Hawaii, the amateur telescopes that spotted Borisov, the Atlas survey in Chile, represent new capabilities. The discoveries coincide with technological thresholds, not with cosmic planning. That argument carries weight. But even within that framework, the clustering of events is striking. 3 major interstellar detections so close together. Models revised not once but repeatedly to accommodate them. Natural coincidence is still coincidence, and too much of it begins to feel like something else. Cosmic timing also matters for survival. If Atlas is natural, then its billions of years of wandering without destruction suggest a kind of lottery win. The galaxy is violent, yet it passes through undamaged until now. If it is artificial, then its arrival now may be precisely because this is the moment it was meant to appear. Technology does not last forever, not even advanced technology. To endure billions of years, a probe would require maintenance, repair, or renewal. If Atlas is one of many, then perhaps they are dispatched in waves, each wave timed to sweep through systems on a schedule. In that light, the coincidence of 3 visitors in a decade looks like the leading edge of a pattern we cannot yet see. The worst-case scenario here is not impact or destruction, but intention hidden behind timing. If these objects are scheduled probes, then we are not random witnesses, we are the subjects of observation. The coincidence of detection aligns with the coincidence of being worth observing. That realization is not comforting. It suggests that the timing is not ours, but theirs, that what feels like chance is in fact calibration. We are being measured against a clock we did not set. Consider how humanity might behave in the same position. If we detected a young civilization on a distant world, just beginning to build telescopes, we might send probes disguised as natural objects. We would time their arrival so they coincided with the species' ability to see them. We would want to watch the first reaction. Do they recognize anomalies? Do they search for patterns? Do they assume natural explanations? Timing would be everything, because only at that stage is the data valuable. Too early, and the probes would be ignored. Too late, and they would be intercepted. The parallel is uncomfortable. The timing of Atlas, following the timing of Oumuamua and Borisov, feels too convenient. And yet, there is always the possibility that coincidence is all it is. That the galaxy is simply full of interstellar objects, and our detection capabilities have just now reached the point of discovery. The clustering is luck, nothing more. If so, then the worst case is not intention, but misunderstanding. That we twist coincidence into narrative because we crave meaning. The human mind is built to find patterns, to tell stories from randomness. Perhaps the timing means nothing, and we are the ones imposing design where none exists. But even if so, the unease remains, because the numbers still do not align, and luck stretched too far begins to look like plan. The truth is that cosmic timing will always be ambiguous. We cannot know whether 3 visitors in 10 years is coincidence or design, because both explanations remain plausible. If we detect 10 more in the next decade, the coincidence grows harder to dismiss. If none arrive, the timing looks stranger still. Atlas may not settle this question, it may only sharpen it. We are left with possibilities, each unsettling in its own way. Coincidence undermines our models, forcing us to admit our ignorance. Design undermines our assumptions, forcing us to confront the possibility of being observed. Both leave us with doubt, and doubt is the one constant in these encounters. Atlas races along its path, its timing perfect or meaningless, depending on how we choose to see it. It arrived now, in this era, in this narrow window when humanity has the tools to notice. That fact is undeniable. Whether it is coincidence or design remains the open question, and in that uncertainty lies the true worst case. Because if the timing is coincidence, it shows us how little we understand, and if it is design, it shows us how little control we have. The simplest explanation for 3I/A TLAS is that it is a comet, an icy body ejected from its home system billions of years ago, drifting through the galaxy until chance carried it near the Sun. That explanation satisfies the cautious majority of scientists because it requires no extraordinary claims. Yet the anomalies linger, its unusual chemistry, its extreme speed, its improbable survival, its ambiguous size. Taken alone, each can be dismissed as an edge case of natural processes. Taken together, they invite darker speculation. One of the most unsettling ideas is that ATLAS may not simply be drifting. It may not even be active in the way we think. It could be a probe waiting to wake. To imagine such a thing, consider the challenge of interstellar travel. A machine intended to cross billions of kilometers, or even billions of years, cannot remain active continuously. Power would drain, systems would degrade, signals would be lost. The only strategy that makes sense is dormancy. Sleep until the conditions are right. Hibernate until a star's warmth or a planet's signals trigger awakening. In this way, a probe could last not centuries but eons, not light years but galactic revolutions. Waiting to wake is not inefficiency, it is survival. What would such a probe do upon waking? The possibilities divide into two broad categories: observation or action. In the first, it might do nothing more than gather data, quietly recording emissions, atmospheres, or planetary signatures. In the second, it might release something smaller, something designed to land, seed, or signal. Neither outcome requires visible evidence. Both could occur unnoticed within the glare of a coma. For all our telescopes, we cannot see beneath the shroud of gas and dust. If Atlas is more than natural, its dormancy and its waking would be invisible to us. The troubling part is timing. Why now? Why here? If Atlas has been asleep for billions of years, what determines when it wakes? The simplest trigger is proximity to a star. As it approaches the Sun, heat penetrates its crust, volatiles sublimate, and activity begins. To us, that looks like cometary behavior. To a disguised probe, the same trigger could also power hidden systems, charging batteries, activating instruments, initiating transmissions. Outgassing could serve as both cover and function, concealing activation behind a mask of natural chemistry. To our instruments, nothing would look unusual. To the probe, everything would be coming online. This possibility transforms the coma itself into a signal. Each plume of gas, each burst of dust, could mask something deliberate. Antennae unfurling, sensors activating, processors spinning up after a billion-year sleep. The disguise is perfect because it requires no deception. It simply uses natural processes as camouflage. We assume sublimation, and we are not wrong, but we might not see what rides beneath it. A machine could sleep as ice for eons, then wake as gas carries its activation forward. The very thing we call natural could be the instrument of intent. If this is the case, then humanity has already missed its chance. We cannot see through the coma. We cannot intercept the nucleus. We cannot hear what it might transmit. We are spectators, locked out of whatever awakening is occurring. Our only data will be indirect, brightness, spectra, orbital plots. If a probe has awakened, it will finish its tasks and depart before we can confirm. The worst case scenario is not that Atlas wakes violently, but that it wakes quietly, and we never know. There is also the possibility of delayed activation. A probe might not wake upon approach to the Sun, but only after passing perihelion, when its trajectory ensures escape. In this way, it could gather data, compress it, and transmit once it is safely outbound, out of range of interference. The disguise remains intact until the moment it no longer matters. By the time we wonder whether it woke, it is already gone, carrying with it whatever it learned. To us, the silence remains. To whoever launched it, the mission continues. Skeptics argue, of course, that this is nothing more than projection. We imagine dormancy and awakening because they mirror our own designs. Our spacecraft hibernate to conserve power. Our missions rely on triggers and timed activations. We impose our strategies on the unknown. That critique is valid, but it does not erase the possibility. If dormancy is the only logical strategy for endurance, then it is likely universal. It is not a human solution. It is a solution to physics itself. Any long-lived probe must, by necessity, wait to wake. The unsettling implication is that Atlas may not be unique. If it is a probe, then it is one of many. Each one launched into the galaxy, disguised as comets, dormant until triggered. Each one passing through star systems unnoticed, except when conditions align. If so, then the galaxy could be filled with sleeping machines, silent now, waiting to wake when stars warm them, when signals reach them, when the right species emerges. Atlas is only the one we see. The others pass without notice, invisible in the dark. From this perspective, the arrival of 3 interstellar objects in less than a decade takes on new meaning. Perhaps it is not coincidence. Perhaps we're in a region of the galaxy seeded with sleepers, machines drifting silently until they encounter systems of interest. Perhaps Earth lies within a mapped corridor, a route designed to ensure observation of emerging civilizations. If so, then each detection is not chance but schedule. Oumuamua, Borisov, Atlas. Each one an awakening timed to coincide with our ability to notice. We think we are observers. Perhaps we are the observed. The worst-case scenario is not invasion. It is irrelevance. If Atlas has awakened, it may not care about us at all. Its mission may be broader, designed to gather galactic data, catalogue environments, measure stellar activity. We may be incidental, or worse, we may already be part of a catalogue, entered without our knowledge into records that stretch across billions of years and countless civilizations. To realise we are data in someone else's archive is more humbling than any direct contact could be. It strips away the illusion that we are early explorers. It shows us we are latecomers to a galaxy already mapped. And yet, there is one more unsettling thought. What if awakening does not mean gathering, but seeding? A dormant probe could carry spores, microbes, nanomachines, any form of replicator small enough to survive. Upon activation, it could release them into planetary systems, seeding life or altering environments. If so, then the chemistry of Atlas is not just anomaly, it is payload. The gases we measure may not be sublimation at all, but controlled dispersal. We assume we are safe because the object does not threaten collision. But collision is not required. Proximity is enough. A machine that waits to wake does not need to strike. It only needs to exhale. Whether we accept this speculation or not, the concept of a probe that waits to wake is sobering. It reminds us that dormancy is a strategy we cannot detect, and awakening may already be occurring beyond our perception. Atlas may be only ice and dust, a survivor of chaos, a relic of planetary birth, or it may be more, a sleeper designed to rise at just the right time. In either case, we cannot know. That ignorance is itself the danger. We look, we measure, we argue. But if Atlas is a probe, its awakening does not require our recognition. It only requires the silence we provide by dismissing it. And so Atlas passes, perhaps asleep, perhaps awake. Its coma expands, its orbit curves, its path ensures departure. We watch, but watching may not matter. If it was meant to wake, then it already has. If it was meant to observe, then it already has. If it was meant to seed, then it already has. The truth will slip away with it, vanishing into interstellar night. All we are left with is speculation, the haunting possibility that we were not watching a comet at all, but a probe designed to wait, designed to wake, designed to leave us wondering. The silence of 3i Atlas is what reassures astronomers the most. No signals, no transmissions, no evidence of technology. Just ice, dust, and gas behaving as comets should, at least on the surface. Yet silence is not always comfort. In some interpretations of cosmic sociology, silence is the only survival strategy. This idea is often called the dark forest hypothesis, a metaphor drawn from a place where countless hunters stalk the woods, each knowing that to announce themselves is to risk discovery by predators. In such a galaxy, the safest civilization is the quiet one, the one that hides, the one that does not send signals. Within that context, the silence of Atlas is not an absence. It is the very thing that makes suspicion reasonable. In a dark forest, every movement is dangerous. Sending radio messages into space, shining beacons across the stars, broadcasting your existence is like lighting a fire at night in hostile terrain. It draws attention. You cannot know who will see, and you cannot know whether they will be friend or predator. If the galaxy truly functions this way, then every civilization that survives long enough to build technology also learns to hide. They camouflage their worlds, mask their energy signatures, encrypt their signals and retreat into silence. And if they explore, they do so under disguise, sending machines that look like natural objects. In such a scenario, an interstellar visitor like Atlas fits perfectly. Not a broadcast, but a whisper hidden inside silence. Not a ship, but a comet. The unsettling part is that this strategy does not require malevolence. It requires only caution. Civilizations might not be predators at all. They might simply fear predators. And in that fear, they act as though the galaxy is hostile, even if it is not. Silence becomes the default. Camouflage becomes the rule. If so, then the galaxy we see, quiet, empty, lifeless, is not empty at all. It is filled with watchers who refuse to speak. Atlas, silent in the radio spectrum, disguised as a comet, fits that rule too well. Its silence becomes the very thing that makes it suspicious. The dark forest idea intersects with Atlas in another way. The hypothesis suggests that civilizations might still signal, but never openly. Instead, they send subtle probes, small machines disguised as debris, passive watchers that drift unnoticed until they encounter a system worth studying. These probes do not announce themselves, they do not transmit loudly, they observe quietly, report later, or not at all. They blend into the background of natural space. If Atlas is such a machine, then it is exactly what a cautious civilization would deploy in a dark forest. This raises a haunting thought. Perhaps we're already surrounded by such probes. Perhaps they pass through constantly, unnoticed, because they look like comets and asteroids. Only now, with advanced surveys, do we start to glimpse them. Each one we detect is debated, explained away, catalogued as anomaly but natural. That is how disguise succeeds. The dark forest does not require that no one is there. It requires only that everyone who is there is hiding. Atlas, in its silence and ambiguity, may be confirmation of that rule. Some argue that the dark forest is too pessimistic. They point out that silence can be explained by natural rarity of life, or by the limitations of our instruments. They suggest that civilizations might not fear predators at all, but simply find no reason to signal. But the pessimistic model remains compelling, because it explains both the lack of signals and the persistence of anomalies. It suggests that what we call coincidence is in fact strategy. It suggests that what we call natural visitors may be observers hidden within camouflage. If so, then Atlas is not an exception. It is a data point in a much larger pattern, one we're only beginning to recognize. The worst-case scenario under this framework is not invasion or destruction. It is the realization that the galaxy is filled with life we will never hear, that every star we see may host civilizations older and wiser than us, all of them silent, all of them hidden, all of them fearful of predators we cannot even imagine. The objects we dismiss as comets may be their instruments. The silence we interpret as absence may be their greatest strength. To live in such a galaxy is to live in ignorance, not because we cannot detect others, but because they will not allow themselves to be detected. For humanity, this scenario creates a dilemma. Do we broadcast, risking exposure, or do we follow the rule of silence, hiding ourselves in turn? So far we have done both. We leak radio waves into space, broadcasting our presence whether we intend to or not. Yet we also debate whether to send deliberate messages, fearing what response they might bring. Atlas's presence sharpens that dilemma. If it is a disguised probe, then it suggests others already know we are here. Our silence would no longer protect us. If it is natural, then its silence still serves as a reminder that survival may require restraint. Either way, the lesson is the same. In the dark forest, the loudest species may not last long. Consider the implications if Atlas is not silent after all, but signalling in ways we cannot detect. Perhaps its emissions are spread spectrum, indistinguishable from noise unless you know the code. Perhaps its signals are directed narrowly, aimed only at a specific point in the galaxy, invisible to us. Or perhaps its communication is not electromagnetic at all, but something we do not yet understand. Gravitational waves, neutrinos, quantum channels. To us, the silence remains. To whoever it speaks to, the message is clear. In the dark forest, communication itself may be layered with disguise. There is another dimension to this. If probes like Atlas exist, they might not only observe but also warn. They might function as alarms, reporting the emergence of civilizations that risk breaking silence. Humanity, with its radio leakage and its attempts at messaging extraterrestrial intelligence, may already be flagged. The arrival of Atlas could coincide with our crossing of a threshold, the point where our signals became impossible to ignore. If so, then its presence is not random. It is response, not an attack, not contact, but observation triggered by our own noise. That possibility is as humbling as it is frightening. The irony is that we may never know which interpretation is true. Silence provides no answers. We listen, and we hear nothing. We speculate, and we cannot confirm. Atlas passes, leaving us with data that fits both natural models and disguised intent. That ambiguity is itself a kind of silence, one that speaks louder than any transmission could. It tells us that the truth, whatever it is, remains hidden, whether by nature's indifference or by intelligence's design. In the end, the dark forest hypothesis forces us to see Atlas differently, not as an anomaly to be solved, but as part of a larger pattern of silence. If the galaxy is truly filled with hidden watchers, then Atlas is only the one we noticed. Its silence is not absence, but strategy. Its disguise is not error, but survival. The worst-case scenario is that this pattern is real, and that we will never escape it, that every interstellar visitor will look natural, behave natural, and leave us wondering. That we will never hear voices because the galaxy has long ago decided that silence is the only way to live. Atlas recedes into the night, silent still. We cannot know if that silence is natural or deliberate. We cannot know if it is the hush of ice or the quiet of intent. All we can do is wonder if, in the dark forest, we have just glimpsed one of its silent hunters, or one of its cautious survivors. When astronomers and philosophers speak of the Great Filter, they refer to the unseen barrier that might explain why the universe appears so quiet. If life is common, and intelligence should emerge many times across billions of stars, then why do we not see signs of it everywhere? The Great Filter is one answer. Somewhere along the path from chemistry to civilization lies a stage so difficult, so improbable, or so dangerous that few ever cross it. Some believe we have already passed it. Others fear it lies ahead. But rarely do we ask what it would look like if it came not as an abstract concept, but as something real, something visible, something drifting through our skies. The arrival of 3i Atlas invites us to wonder whether the great filter might not be theoretical at all. It might be a visitor. It might be standing right here at our doorstep. The filter could take many forms. It might be environmental, a chemical improbability that makes the origin of life exceedingly rare. It might be biological, a tendency for evolution to stall before reaching intelligence. It might be social, a flaw in civilizations that leads to self-destruction before interstellar expansion. But another possibility, one far more unsettling, is that the filter is external, that it is enforced, that civilizations that grow loud enough to be noticed do not last because something else ensures they do not. If that were true, then probes like Atlas may not be explorers or archivists, they may be instruments of the filter itself. This idea does not mean impact or invasion. The great filter does not need to arrive in dramatic form. It could act quietly, invisibly, through observation and subtle intervention. Perhaps civilizations that reveal themselves are catalogued, studied, and monitored. Perhaps when they cross certain thresholds, something follows. The silence of the galaxy might then not be natural but curated. We do not hear others because those who spoke were silenced. If Atlas is part of that mechanism, then we are not looking at a random comet. We are looking at a checkpoint, a reminder that the galaxy is not empty but regulated. The thought is difficult to hold because it paints the universe as less welcoming than we imagine. We like to think of exploration, of meeting others, of joining a community of civilizations. The filter at the doorstep model replaces that hope with caution. It tells us that the very act of noticing Atlas, of debating its nature, might be part of a test we cannot see. It suggests that what feels like scientific discovery could be surveillance. The probe does not need to act now. It only needs to watch, to wait, to decide whether we pass or fail. This interpretation grows sharper when combined with timing. Humanity has only just become capable of detecting interstellar visitors. Our radio leakage into space has been spreading for less than a century. Our digital signatures, our artificial satellites, our global networks are barely older than a human lifetime. If there were ever a moment when we might draw attention, it is now. And just as this happens, just as our technologies awaken, we see Oumuamia, then Borisov, then Atlas. Coincidence, perhaps, or schedule. A series of probes passing through to confirm which species have begun to rise, which are ready to be filtered. What form would such filtering take? It does not have to mean annihilation. It could mean containment, ensuring that young civilizations never expand beyond their stars. It could mean discouragement, subtle interventions that derail progress. It could mean cataloguing, deciding which to allow and which to stop. Or it could mean something we cannot even define, an outcome beyond our comprehension. The Great Filter may not be a single event, but a process that repeats across the galaxy, invisible to those who have already been silenced. The silence we observe may not be mystery at all, but evidence of its success. Atlas, in this light, is more than anomaly. It is symbol. It embodies the possibility that the galaxy is structured not by chance, but by oversight. Its speed ensures it cannot be caught. Its coma conceals its core. Its silence hides intent. Each feature makes sense for a machine designed not to communicate, but to observe. If the Great Filter operates through probes, then they must appear natural, unremarkable, deniable. They must be ambiguous enough that civilizations explain them away, even as they are studied. That is how control is maintained, through uncertainty. The worst-case scenario is not that Atlas destroys us. It is that Atlas proves we are already inside a managed system, that the galaxy is not an open frontier but a controlled forest, where rules are enforced not by chance but by long-standing design. To discover this would be to realise that our fate is not fully our own, that survival depends not only on what we do, but on whether we are allowed. That is what it means for the great filter to be at our doorstep. And yet there is another way to see it. Perhaps probes like Atlas are not enforcers but warnings. Perhaps they are reminders that survival is fragile, that the universe is hostile, that the real filter is not imposed but endured. Radiation, collisions, supernovae, black holes. These are dangers enough. Perhaps Atlas tells us that survival requires more than chance, that we must plan, adapt and endure as it has. In this interpretation, the filter is not external judgment, but cosmic reality. To survive is to defy odds, and Atlas is proof that survival is possible. But the ambiguity remains. We cannot know which interpretation is true. All we know is that the object is here, now, visible in our skies. Its chemistry does not fit. Its speed defies expectation. Its origin lies in the ancient thick disk older than our world. It carries silence as its signature, and it passes just as humanity becomes capable of noticing. That combination is enough to raise the question whether or not the answer exists. The great filter has always been theoretical, a way to explain absence. But what if absence is not absence at all? What if the silence is active, the result of choices made long before us? What if every interstellar visitor is a messenger of that silence, a subtle reminder that we are not alone, but that being noticed is not the same as being welcomed? Atlas forces us to confront that possibility. Its presence makes the abstract tangible. The filter might not be distant, it might already be here. And so Atlas continues its flight, outward bound, leaving us with nothing but data and speculation. We debate its nature, we publish our models, we assure ourselves it is only a comet. But the doubt lingers, because in that doubt lies the darker possibility that the great filter is not in our past or in our future, but already at our door, and Atlas, silent and swift, might be the first knock we have heard. When we look at 3i Atlas, we see a small visitor traced against the black of space, its tail stretching faintly, its path predictable, its time here fleeting. We see dust and ice, a chemical fingerprint, an orbital arc. But behind those numbers lingers a deeper question. If this object is not natural, or even if it is, what does it represent? Is it only debris? Or is it something more? A relic, not just of a star system, but of the minds that once existed there? When we speculate about probes or disguises, we are also speculating about civilizations. And if Atlas is in any way artificial, then it may not belong to the living. It may be the ghost of a civilization long gone. The galaxy is old. Our own solar system has existed for 4.5 billion years, yet the Milky Way is more than twice that age. The thick disk from which Atlas may have originated dates back to 10 or 12 billion years. In that time, entire cycles of creation and destruction could have unfolded. Civilizations might have risen, flourished, expanded and disappeared before the sun was born. Their technologies might remain, drifting through space long after their creators vanished. Atlas could be one of those remnants, a silent machine carrying not only instruments but memory, the last trace of beings who no longer exist. The unsettling part of this idea is its plausibility. We know from our own history how fragile civilizations can be. Empires rise and collapse in centuries. Languages vanish, cultures disappear, knowledge is lost. We extend this fragility forward into cosmic timescales and realize how unlikely it is for any civilization to endure for billions of years. But technology endures differently than biology. Machines can outlast makers. Probes can travel after their builders are dust. In this way, the galaxy could be haunted not by living beings but by their creations. Each interstellar object we discover may be more than ice. It may be a monument to those who came before, who tried to reach beyond their stars, who left behind artifacts mistaken for comets. The ghost hypothesis is both comforting and terrifying. Comforting because it suggests we're not alone, that others once existed, that intelligence is not unique. Terrifying because it also suggests extinction is inevitable. If Atlas is a ghost, then its makers are gone. Their silence is not strategy, but finality. We would then be looking not at explorers, but at tombstones. And the worst case scenario is that our own future is written in theirs, that we too will leave behind relics mistaken for natural objects, silent witnesses drifting through the galaxy long after we're gone. Consider what it means for a probe to survive its civilization. Without contact, without maintenance, without updates, it would become autonomous by necessity. Its mission would continue until its systems failed, until time erased its functions, until disguise became indistinguishable from decay. But if designed for endurance, if built to last across cosmic epochs, it might still operate, carrying out instructions written billions of years ago. It may not matter that its makers are gone. The mission might be all that remains of them. Atlas could be a ghost not just in symbolism, but in practice. A machine still following commands from masters who no longer exist. If so, what commands would endure? Observation is simple. Measure radiation, catalogue atmospheres, record chemistry. These tasks do not require contact, do not require decisions. They can be repeated endlessly. A ghost probe would wander, collect, and perhaps transmit, though transmit to no one. Its signals may go unanswered, its data never received. It would become ritual, function without audience, persistence without purpose. Yet from our perspective, it would still appear alive, still appear deliberate. The haunting part is that its activity would look the same whether its civilization thrived or perished. We could not tell the difference. This ambiguity deepens the mystery. If Atlas is natural, then it is a survivor of cosmic violence. If it is artificial, it may be a survivor of civilizational violence, extinction. Either way, it carries survival as its defining trait. But survival of what? Matter? Mission? Memory? If the galaxy is populated by such ghosts, then every interstellar visitor is more than an anomaly. It is history embodied, a piece of evidence that civilizations existed, even if we will never know their names. The ghosts pass us silently, and we do not recognize them. Some may argue that ghosts are only metaphors, that machines cannot carry spirit, only function. But even function is enough. A probe like Atlas, if artificial, is not just a machine. It is the residue of minds that thought, planned, and built. It is their continuation, however faint, across time they themselves could not witness. When we look at it, we may be looking directly at the handiwork of intelligence from 10 billion years ago. That alone makes it a ghost, an echo of presence, a whisper of something no longer there. The thought grows darker when combined with the great filter. Perhaps civilizations do not survive, but their machines do. Perhaps the galaxy is not empty but littered with remnants. Ghost probes drifting in disguise, fragments of once great species reduced to silence. We mistake them for comets, but they are memorials. If so, then the future is clear. We too will leave behind our voyagers, our pioneers, our satellites, drifting endlessly after we are gone. And if another civilization finds them, they will ask the same question we now ask of Atlas. Was this natural, or was this a ghost? The worst case scenario here is not collision or invasion, but realization. That the galaxy is filled with civilizations, but only in the past tense. That intelligence emerges often, but never survives. That the silence we hear is not absence, but aftermath. Atlas, then, is not a threat, but a reminder. A ghost drifting by to show us what awaits if survival proves impossible. Its very presence is a warning, silent but powerful. Others were here, and they are gone. Yet there is another possibility. Ghosts may not be passive. If a probe like Atlas is still functional, it may still carry influence. It might seed life, spread chemistry, alter worlds in ways its makers intended. If so, then the ghosts of civilizations past are not only memories but participants, shaping the galaxy long after their own extinction. In that sense, they are not gone at all. They live on through their machines, their legacy etched into every system they pass. Perhaps even life on Earth owes its origin to such interventions, seeded by ghost probes long forgotten. The irony would be profound, that our own existence is the product of civilizations that did not survive, that we are their continuation without knowing it. But again, ambiguity wins. We cannot know if Atlas is only ice, or if it is something more. We cannot know if it is natural survivor or artificial ghost. All we can do is wonder, and wondering is what makes it haunting. Because ghosts are defined not by their presence, but by our inability to explain them. They are the things that remain when explanation fails. Atlas fits that definition too well, and so the object moves on, fading from our instruments, leaving us with silence and speculation. If it is a ghost, then it has fulfilled its purpose, not to communicate, not to act, but simply to remind us that we are not the first to wonder. The galaxy is old. Civilizations rise and fall. Their remnants drift forever. Atlas may be one of them, a messenger not of life, but of its inevitable fragility. The ghosts of civilizations past are out there, and one of them may have just passed by our world. When scientists look at comets, they often see more than frozen relics of planetary birth. They see possibilities. Comets carry water, organics, and complex molecules. They preserve the chemistry of ancient disks in deep freeze, delivering those compounds when they strike young planets. This has long inspired the theory of Panspermia, the idea that life or its building blocks travel through space, spread by collisions, drifting dust and icy messengers. If 3i Atlas is natural, then it may be one such messenger, a carrier of chemistry from a star system older than our own, now shedding gases into the inner solar system. That thought alone is profound. But speculation does not stop there, because if comets can deliver life, they can also deliver death. Panspermia may not be a gift, it may be something worse. At its most optimistic, Panspermia suggests that life is universal, that the molecules of biology, the seeds of cells, drift from star to star, carried across light years by survivors like Atlas. A young planet receiving such material might gain a head start toward biology. Life might not need to emerge anew in every system. It might only need to take root when the right chemistry arrives. If this is true, then we may all share ancestry not only across Earth, but across the galaxy. The DNA that builds us may have kin on worlds around distant stars. Atlas, then, would not just be a curiosity, it would be family. But Panspermia has darker implications. If life can spread, so can disease. Microbes can survive astonishing extremes. Vacuum, radiation, freezing cold. Extremophils on Earth demonstrate resilience we once thought impossible. If organisms can survive ejection into space, shielded inside rock or ice, then Panspermia may carry more than building blocks. It may carry active biology. And if so, then every interstellar visitor is not just chemistry. It is risk. Atlas could in theory carry organisms unknown to Earth, adapted to conditions we cannot imagine, capable of disrupting ecosystems in ways we cannot predict. The very mechanism that spreads life could also spread extinction. For this reason, scientists debate whether Panspermia is blessing or curse. Some propose that life on Earth began this way, seeded by comets rich in organics. Others caution that if life can spread, it may also overwhelm. If civilizations exist, they might use the principle deliberately. Instead of sending ships, they might send seeds, genetic payloads designed to alter environments, replicate, and dominate. Such strategies would be cheaper and longer lasting than fleets. A probe disguised as a comet could carry spores, microbes, or engineered replicators, releasing them quietly into planetary systems. To us, this would look like natural outgassing. To them, it would be seeding. The idea that Atlas could be such a vehicle is difficult to dismiss entirely. Its unusual chemistry already defies expectations. Its survival across billions of years suggests durability beyond chance. If it is artificial, its purpose might not be observation alone, it might be dispersal. A single object, drifting unnoticed, could carry seeds of biology across systems, spreading life or reshaping it. Panspermia, or something worse, evolution driven not by chance, but by deliberate engineering. This brings us to the question of intent. Natural panspermia is indifferent. Life spreads where it can, surviving by chance. But artificial panspermia introduces design. What if Atlas is not carrying random molecules but carefully chosen ones? What if the organics it vents are not remnants of formation but instructions encoded in chemistry? Such a probe could alter the course of worlds, introducing traits, driving evolution, shaping ecosystems. It would be gardening on a galactic scale, but it would also be manipulation. If Earth itself were seeded this way, then our biology might not be entirely our own. We might be products not of chance but of an ancient program, written long ago, still running through relics like Atlas. The darker version of this possibility is weaponization. Panspermia need not bring life, it could bring sterility. A probe could release chemistry that disrupts DNA, poisons atmospheres, or sterilizes surfaces. This is not far-fetched in principle. Microbial warfare exists even on Earth, where one species evolves to suppress another. On cosmic scales, such strategies could be deployed not as war but as filtering, ensuring that emerging civilizations never advance, that young biospheres never threaten. If so, then interstellar visitors are not neutral messengers. They are enforcers. Atlas could be one of them, carrying not life but erasure, disguised as natural while performing a function of control. Skeptics will argue that such ideas are speculative to the point of paranoia, and they are right. There is no evidence that Atlas carries anything more than carbon dioxide and dust. Yet absence of evidence is not evidence of absence. The ambiguity remains. We cannot see inside its nucleus. We cannot intercept its payload. We cannot know whether what it vents is random or designed. We can only admit the possibility, and in that admission, the worst-case scenario takes root. Consider again the numbers. Atlas comes from the thick disk, a population older than Earth itself. If it carries biology, then it may carry biology from a time before our planet even existed. What would such biology look like? Would it resemble anything we know? Would it survive here? Or would it conflict with our own ecosystems, rewriting them in ways we cannot predict? The idea of panspermia often fills us with wonder, but it should also fill us with caution. To accept material from an object this ancient is to invite something alien into our world, and yet perhaps it has already happened. Comets have struck Earth countless times across its history. Impacts deliver not only destruction but chemistry. Some argue that the ingredients for life itself arrived this way, delivered by icy messengers billions of years ago. If that is true, then panspermia is not theory. It is our origin. We are already the product of it. Which raises another unsettling possibility, that panspermia is not random at all, but orchestrated. That life across the galaxy is seeded intentionally, guided along a program written not by chance but by civilizations long gone. If so, then Atlas is not the first seeder we have encountered. It is only the latest. The worst-case scenario here is layered. If Atlas is natural, it may still carry organics that alter our understanding of life. If it is artificial, it may carry design, biology meant to seed or suppress. Either way, it confronts us with the fragility of our assumptions. We imagine life as ours alone, Earth as unique, biology as local. But Atlas reminds us that the galaxy may be far more connected and far more dangerous than we wish to believe. For humanity, the lesson is clear. We cannot assume that interstellar visitors are neutral. We cannot assume that panspermia is only blessing. We must consider the possibility of something worse. Because once an object passes through, once it vents its chemistry, once it disperses its dust, we have no defense. We cannot filter space. We cannot intercept every visitor. We are exposed, and exposure means risk, whether that risk is life's beginning or life's end. And so Atlas continues its passage, shedding carbon dioxide, glowing faintly against the night. To most it is only a comet, another icy body burning briefly before fading. But to those who speculate, it is something more, a potential messenger, a potential threat, a potential ghost. Panspermia, or something worse, we cannot know. All we can do is watch as it passes and wonder what it leaves behind. When people imagine an invasion from the stars, they picture fleets of ships, blinding lights in the sky, weapons far beyond our comprehension. The stories we tell ourselves lean towards spectacle, because spectacle is what captures fear and awe. But in reality, an invasion need not be dramatic. It need not arrive in force or in fire. It could arrive quietly, invisibly, carried inside dust grains, riding the tails of comets, spreading not through armies but through chemistry. It could arrive as microseeds, particles too small to see, too simple to recognize, drifting down into atmospheres and oceans without resistance. If so, then silent invasions may already have taken place, not through conquest, but through the quiet persistence of biology, or something that only appears to be biology. Atlas, with its shroud of gas and dust, presents a stage for this possibility. We know that comets shed material as they approach stars, releasing plumes of volatile compounds that spread into surrounding space. The Earth itself has passed through cometary debris countless times, the particles burning as meteors in our skies, some surviving to reach the ground. If Atlas carries anything more than dust, then it too may be capable of dispersal. And if what it carries is not just chemistry but engineered microseeds, then we face a form of contact we are unprepared to recognize. A microseed does not have to be alive in the way we define life. It could be self-assembling molecules, fragments that replicate under the right conditions. It could be nanostructures designed to activate when exposed to certain energies. It could be something between biology and machine, too alien for us to categorize. Our instruments would likely record them as dust or as noise, dismissing them as contamination. Yet once inside a planetary environment, they could become more, taking root in soil, air or water, altering ecosystems quietly, invisibly, over generations. This concept reframes invasion. It is not about territory or dominance, but about infiltration. It does not require fleets or battles, only patience. A civilization wishing to spread across the galaxy could do so without ever travelling physically. It could release swarms of microseeds disguised as cometary ejecta, letting them drift from system to system, seeding or replacing biology wherever they land. Over billions of years, such dispersal could cover the galaxy, one invisible invasion at a time. Atlas could be one such vector, a delivery system mistaken for natural, its tail carrying not randomness but intent. The troubling part is that this possibility does not require malice. It could be simple survival. A civilization facing extinction might choose to seed the galaxy with micro-replicators, ensuring some form of its biology endures. To them, this would not be invasion but legacy. To us, it would feel like intrusion. Our biosphere could be altered without our knowledge, rewritten by fragments of design older than our world. We would never know until it was too late, and even then we might not recognize the source. History on Earth shows how silent invasions occur even without cosmic scales. Microbes have travelled with humans across continents, carried unintentionally in ships and trade, devastating populations unprepared for them. Species introduced into ecosystems spread uncontrollably, displacing natives, transforming landscapes. These invasions are rarely dramatic in the moment, but their consequences are profound. Extend this principle to galactic scales, and the same logic applies. Microseeds need not be numerous or powerful, they only need to survive, replicate, and wait. Time does the rest. If Atlas is only a comet, then its dust is harmless, ordinary, no more threatening than any other fragment of cosmic debris. But if it is a probe, if its chemistry is disguise, if its mission is dispersal, then every plume it vents may be seeding. We measure carbon dioxide in its spectrum, but we cannot see what else hides beneath. Spectroscopy reveals signatures of molecules, but not the intent encoded within them. A microseed could ride in silence, indistinguishable from natural dust, only to activate when it finds a suitable host. The disguise would be perfect, because the distribution looks natural. Our own planet may already have received such visitors without our awareness. The worst-case scenario is not that Atlas carries weapons in the traditional sense, it is that it carries seeds of change. A silent invasion does not need to destroy, it only needs to overwrite. It replaces what exists with something else, gradually, quietly, invisibly. It does not matter whether that something else is biology, nanotechnology, or chemistry. What matters is that it takes root where it is not wanted, and once rooted, cannot be undone. A civilization might never know it had been invaded until its world no longer resembled what it once was. Skeptics will point out that we have no evidence for such dispersal. They are right. But absence of evidence is exactly the point. Silent invasions would succeed precisely because they remain undetected. If Atlas is natural, then it fits no narrative of malice. If it is artificial, then its effectiveness lies in ambiguity. We can dismiss it as cometry, as debris, as anomaly, and in that dismissal it succeeds. A microseed invasion does not require us to notice. In fact, it depends on us not noticing. This possibility raises uncomfortable questions about our own actions. When we send probes beyond Earth, when we release spacecraft that may one day cross into interstellar space, are we not also carrying microseeds? Not deliberately perhaps, but microbes cling to surfaces, survive sterilization, endure extremes. Our machines may already be carrying Earth life outward, unintentionally seeding other systems. From another perspective, we might be the silent invaders, unaware of the consequences of what we release. If we can do this without meaning to, what might others achieve if they mean to? The ambiguity of Atlas reinforces this unease, its speed, its chemistry, its survival, its silence. All can be explained naturally, but they can also be explained strategically. A probe disguised as a comet, shedding dust that carries seeds, fits too neatly into what a cautious, long-lived civilization might deploy. It requires no confrontation, no risk, no communication. It is invasion without contact, spread without war, victory without awareness. That is the true nightmare of microseeds and silent invasions. They succeed not because they overpower, but because they are ignored. The galaxy may already be filled with such invasions. Life itself may be the product of them, spreading not by chance but by ancient design. Our biology may not be ours alone, but the accumulation of countless dispersals across billions of years. Atlas may then not be unique but typical, one of many seeds drifting endlessly. If so, then invasion is not future speculation but past reality. We are already products of it, shaped by it, unable to separate ourselves from it. The line between natural panspermia and deliberate seeding blurs until it disappears. What we call biology may already be invasion, long completed, and yet the worst case grows even darker. Because if Atlas carries microseeds, they may not be meant to coexist. They may not be biology as we know it. but something designed to replace biology altogether. Nanostructures that consume organics, self-replicators that dismantle DNA, chemistries that operate on principles alien to ours. To us, they would be invisible until they were everywhere. By the time we noticed, it would be too late. Silent invasions succeed not because they are fast, but because they are patient. And patience is something the galaxy has in abundance. As Atlas moves through our skies, shedding its veil, drifting along its arc, we cannot know what it carries. To most, it will always be a comet, unusual but natural. To some, it is something else, a messenger, a ghost, a probe, a threat. Whether it is Panspermia or something worse, whether it is natural or designed, whether it is harmless or invasion, the ambiguity is the point. Silent invasions succeed when debate replaces certainty, when doubt prevents action, when the object is dismissed as anomaly while it does its work. Atlas, in its silence, may already embody that principle. And so we watch it pass, knowing that if it carries seeds, they are already scattered. If it is invasion, it is already silent. The object leaves us with nothing but questions, and questions may be the only evidence we will ever have. Because in the galaxy, the loudest invasions are easy to resist. The silent ones are the ones that endure. Every discussion of Three-Eye Atlas eventually circles back to the same possibility. If it is only ice and dust, then it is nothing more than a curiosity of nature, strange but natural, fleeting but harmless. But if it is more than that, if it is artificial, if it is in any way designed, then its most likely role is not to act, but to watch. It would not need to announce itself or interfere directly. It would not need to land or signal. Its function could be as simple as observation, passing silently through our system, gathering information, then disappearing again into the dark. That is the possibility that lingers most heavily. Because if Atlas watches, the question becomes unavoidable. What does it see? To answer that, we must first imagine the perspective of such a watcher. From its position in interstellar space, it would not view Earth as we see ourselves. It would see a planet glowing faintly in reflected sunlight, wrapped in thin layers of atmosphere, dotted with electromagnetic noise leaking into space. Its sensors would measure chemistry, scanning for oxygen, nitrogen, methane, carbon dioxide. From those gases alone, it would know that Earth is not barren. It would recognize disequilibrium, oxygen levels sustained only by biological activity, methane present despite its tendency to break down. That single signature, even without radio leakage, would be enough to reveal life. But Atlas, if it watches, would see more than life. It would see civilization. Our radio signals, weak as they are, stretch into space for about a century's radius. They are faint, yes, but not non-existent. To sensitive instruments, the glow of radio, television, radar and satellites forms a detectable halo. Earth is no longer silent. We have betrayed ourselves through leakage. A probe passing by now at the right distance could confirm what natural spectra already suggest, that this is not only a living world, but one where intelligence has emerged. If Atlas is a watcher, then it already knows this. The unsettling part is what else it might notice. Our atmosphere contains traces of pollution, chlorofluorocarbons, industrial chemicals, isotopes from nuclear activity. These are not natural markers. They are signatures of technology, signs that a species here has harnessed industry and power. Even without listening to our broadcasts, an observer could read this directly from air. The Earth reveals itself through chemistry. If Atlas measures, then it sees not only biology but industry, not only life but civilization. It sees us. And what would it conclude? That depends on intent. A neutral watcher might simply catalogue. It would add us to a database of worlds, noting our stage of development, comparing us to others, measuring our trajectory. An analytical watcher might assess risk, calculating whether we are dangerous, whether we are likely to expand, whether we will disrupt galactic silence. A strategic watcher might do more, considering whether intervention is necessary. From our perspective, we cannot know which it is. All we can know is that if it watches, it does not miss the obvious. Earth glows with signatures no natural world could produce. Some argue that this is paranoia, that even if probes exist, they would not care about us. But history shows that the act of watching is never neutral. To watch is to value knowledge. To value knowledge is to plan how to use it. If Atlas is truly observing, then we are part of its purpose. The only question is whether we are its subject of curiosity, its subject of study, or its subject of strategy. The difference between those outcomes is enormous, but from our side they all look the same. Silence. The problem deepens when we consider scale. If Atlas is one of many, then Earth may have been watched before, perhaps many times, perhaps long before we had the ability to notice. The first watchers would have seen a planet filled with forests and oceans, but no machines. Later watchers might have seen early humans, their fires glowing faintly, their numbers small. Now a watcher sees cities, satellites, networks, signals. From its perspective, Earth is a rapidly changing world. Civilization has risen in the blink of an eye, and with it, risk. That sudden change would be unmistakable. Atlas, if it watches, would know that something has shifted here in a way worth noting. The worst-case scenario is not simply that we are being watched, but that we are being evaluated. Observation is rarely passive. It often leads to judgment. If probes like Atlas are scattered across the galaxy, each watching young civilizations, then their purpose may be to decide which ones matter, which ones survive, which ones are ignored, and which ones are silenced. The silence of the galaxy would then not be absence, but consequence. Civilizations rise, watchers record, judgments are made, outcomes follow. If so, then Atlas does not simply see us, it assesses us. And we cannot know by what criteria. The idea that we are under surveillance changes how we must think of ourselves. We often imagine exploration as one day reaching out, becoming the watchers. But if Atlas is real, then that stage has already passed. We are not the first, we are not the explorers, we are the explored. To accept that is to accept that our story may already be part of someone else's archive. That what we consider progress, our telescopes, our radio waves, our satellites, are nothing more than markers logged by a passing probe. If it watches, then we are already part of a data set far older and far larger than ourselves. And what would that data set show? From the perspective of Atlas, Earth is unstable. Our atmosphere reveals rapid change. Carbon dioxide levels are climbing sharply, methane rising, ozone shifting. In a geological instant, our planet has transformed. A watcher might not see this as progress, but as crisis. It might see a species altering its environment at dangerous speed, destabilizing its climate, threatening its biosphere. To us, this is environmental concern. To an observer, it may be evidence of a species that cannot control itself. If it watches, then it may already see us as a civilization on the edge. The ambiguity here is the most haunting, because we cannot know what it sees, and we cannot know how it interprets. What looks like pollution to us may look like technology to it. What looks like crisis to us may look like potential. We do not know whether it sees danger or opportunity, threat or promise. We cannot know because we cannot step outside ourselves. We can only imagine its perspective, and in that imagining lies fear. Because if Atlas watches, its judgment is invisible. It does not announce itself. It does not tell us what it sees. It only observes, silently, as we reveal ourselves. The worst-case scenario is not invasion. It is irrelevance, that Atlas watches and sees us clearly, but concludes that we are unimportant, that it logs us as one of many, destined to rise briefly and fall as others have before, that our signals and our industry are not unique but typical, just another line in a record stretching back billions of years. The realization that we are ordinary in the eyes of a watcher is more unsettling than the fear of attack, because it tells us we do not matter. We are not the beginning of history, we are a footnote in a story already written. And yet, perhaps it is worse if we do matter. If Atlas sees us not as ordinary but as a problem, a noise in a galaxy that prefers silence, then its judgment may not be passive. It may not act itself, but it may signal others or trigger systems we cannot perceive. The galaxy may enforce rules we do not know, rules we cannot break without consequence. If it watches and sees us as a violation, then our very visibility may be our undoing. The fact that we notice Atlas only now may itself be part of the sequence. First we become visible, then we are watched, then decisions are made. As Atlas arcs outward, fading into distance, we are left with this question. If it watches, what does it see? The answer is both simple and terrifying. It sees everything. It sees a living planet with industrial chemistry, radio noise, satellites, and a species that has only just begun to look outward. It sees a world changing itself too quickly, a species loud in a galaxy of silence. It sees enough to know we are here. Whether that knowledge matters is the part we cannot know. All we can do is wonder because the Watcher, if it exists, will never tell us what it sees. When Oumuamua was first detected, the scientific community reacted quickly. Telescopes around the world turned to track it, instruments scanned for spectra, and radio observatories listened for signals. The decision to listen, to search for something artificial, was itself an unspoken first response. The world did not debate whether to listen, it simply did. That pattern repeated with Borisov, and again with 3i Atlas. Each time humanity responded with the same set of reflexes: observe, measure, analyze, explain. But beneath those reflexes lies a dilemma that grows sharper with each visitor. If one of these objects were more than natural, if one of them truly were a probe, then what should humanity's first real response be? The dilemma is not only scientific, it is civilizational. A response is never neutral, even when it feels passive. To observe is to reveal ourselves, to track a probe, to direct radio waves at it, to publish our findings, is to acknowledge that we have noticed. If Atlas were only a comet, that acknowledgement is harmless. But if it were a watcher, a disguised emissary, then our attention is a signal in itself. We are saying, "We see you." That message, even if unintended, carries consequences. Because once you recognize a presence, you are no longer invisible to it. The first question is whether we should respond at all. Some argue that silence is safest. If an interstellar object is artificial, then drawing attention might expose us. By remaining quiet, we avoid provoking action. But silence has risks of its own. If the object is watching, then our lack of engagement might be interpreted as ignorance, weakness, or disinterest. In some scenarios, ignorance could be safety. In others, it could be dismissal. A civilization that ignores an emissary might be deemed irrelevant. A civilization that responds might be deemed ready or dangerous. The problem is that we cannot know which interpretation is correct. The second question is how we would respond if we chose to act. Would we attempt communication, sending directed signals toward the object? Would we attempt interception, launching a mission to study it up close? Or would we restrict ourselves to distant observation, hoping to learn without being noticed? Each choice carries risks. Communication could provoke, interception could be seen as aggression, and passive observation could be read as fear. There is no safe option, because safety depends not on what we do, but on how it is interpreted. An interpretation lies with the object, not with us. Consider the possibility of sending a signal. Humanity has debated active messaging for decades. Some scientists support the idea, arguing that if civilizations exist, they must already know about us. Our radio leakage is unmistakable to anyone nearby. Others caution that broadcasting makes us vulnerable, exposing our presence to unknown powers The debate remains unresolved, but with an object like Atlas, the debate becomes urgent. Here is a possible listener close enough to target directly. Do we risk sending, or do we risk letting it pass without attempt? If we send, we may trigger outcomes we cannot predict. If we stay silent, we may miss the only chance we will ever have. The first response dilemma is that both choices feel like gambles. Now consider interception. Some have proposed missions to chase interstellar visitors, fast probes capable of catching up, imaging them, sampling their tails. Technologically, this is barely within our reach. But strategically, interception could be misinterpreted. If Atlas is a probe, then approaching it aggressively might look like hostility. To us, it would be science. To it, it might be defense. A response meant to learn could trigger suspicion. Yet not attempting interception feels like failure, a refusal to seize the opportunity of direct study. Again, both choices feel wrong. Both carry consequences we cannot predict. Even the act of watching is not neutral. By turning telescopes toward Atlas, by following its every move, we are broadcasting intent. The object cannot see our instruments, but it may detect emissions, radar pings, radio sweeps. These betray interest. Interest is information. An intelligent probe could infer our level of technology simply by the nature of our observations. It could measure our curiosity, our caution, our readiness. Every act of study becomes part of the data it gathers. In trying to understand it, we reveal ourselves. In that sense, we have already responded. The dilemma is not future tense, it is present. The worst-case scenario is that our first response matters more than we imagine. If probes like Atlas are common, if they pass through many systems, then each civilization may face the same moment, the choice of silence, signal, or interception. Perhaps the probes exist precisely to test that moment. Perhaps the galaxy's filter operates not through violence, but through evaluation. Civilizations that respond one way may be catalogued as harmless. Civilizations that respond another way may be catalogued as threats. The ambiguity is what makes the dilemma so heavy. We do not know which path ensures survival. We only know that one of them might not. Another layer complicates the dilemma. Humanity itself is not united. No single authority decides our response. Scientists may choose to transmit. Nations may choose to intercept. Observatories may choose to listen or not. Our lack of unity means that any response could be fragmented, contradictory, confusing. A probe watching us might see that disunity as weakness or as danger. It might see us as divided, unpredictable, unstable. If our first response reveals more about us than we intend, then our own internal divisions may be our greatest vulnerability. The dilemma is not only what to do, but who gets to decide. And what if the correct response is none of the above? What if the safest action is to ignore Atlas entirely, to treat it as nothing but cometary debris? That strategy has its risks too. Ignoring a probe may cause us to miss critical warnings, opportunities, or dangers. It may signal apathy or blindness. A civilization that does not recognize what it encounters may not be considered worth further attention. The irony is that every choice, silence, signal, interception, or ignorance reveals something about us. Even indecision is a decision. The probe does not need our communication. It only needs our behavior. The worst-case scenario here is subtle. It is not that Atlas destroys us. It is that Atlas records us, evaluates us, and moves on. That our first response, whatever it is, becomes part of a judgment we will never hear, but which may determine our future. Perhaps not tomorrow, perhaps not in our lifetime, but eventually. If the galaxy is filled with watchers, then each first response matters. Each one contributes to how civilizations are perceived and whether they endure. Atlas may already have seen enough. Our hesitation, our debates, our divided voices, all logged, all assessed, all weighed against criteria we cannot know. And so humanity finds itself in a trap of uncertainty. Do we speak? Do we remain silent? Do we reach out? Do we hold back? The truth is that no choice feels safe. Every option reveals us. Every option risks consequence. That is the nature of the first response dilemma. It is not a question of what we prefer. It is a question of survival in a galaxy we do not understand. And as Atlas passes silently through our system, it leaves us not with answers but with that question, one we must eventually face again, whether we are ready or not. When an unfamiliar object appears in the sky, humanity's instinct is almost always to study it. We point telescopes, build models, write theories. Curiosity is our default state. It has driven every advance we've made, from fire to flight to space itself. Without curiosity, we remain stagnant. Without curiosity, we never grow. And yet, when the object in question is an interstellar visitor like 3i Atlas, curiosity is not the only instinct that rises. Alongside it comes another impulse, quieter but just as old: containment. The need to shield, to defend, to hold back. These two instincts, curiosity and containment, pull against one another, and when the stakes are cosmic, the tension between them becomes a dilemma that feels almost impossible to resolve. Containment is rooted in fear, but not irrational fear. It is the recognition that the unknown can be dangerous. On Earth, when explorers carried microbes to new lands, the results were devastating. Entire populations fell to diseases they could not fight, not through malice, but through contact. History repeats this warning so many times that it has become instinctive. When faced with the unknown, there is safety in restraint. Do not touch, do not approach, do not invite risk. The logic is simple. What you do not disturb cannot harm you. If Atlas carries anything more than ice, then contact may be a danger we cannot anticipate. Containment means refusing that danger, choosing ignorance over exposure. Curiosity, however, rejects that caution. To refuse study is to refuse knowledge. To hold back is to let the greatest mysteries pass us by. Atlas is not only a comet, it is a fragment of another star system, older than Earth, stranger than any sample we have ever seen. To let it go without probing its nature feels like betrayal of what it means to be human. Scientists argue that the risks are negligible, that spectroscopy and imaging from a distance are harmless, that every observation brings us closer to truth. Curiosity insists that discovery is worth danger. That is why we launch probes, why we explore, why we look at the stars. Containment may keep us safe, but curiosity is what moves us forward. When these instincts collide, the question becomes urgent. What if Atlas is more than cometary debris? What if it is a probe, a disguise, a sleeper waiting to wake? Containment would say, do not engage, let it pass. Do not broadcast, do not intercept, do not provoke. Curiosity would say, if we do not engage, we learn nothing. We remain blind. We waste the opportunity of a lifetime. Both sides carry weight, both sides carry risk, and the choice between them defines not just how we respond to Atlas, but how we will respond to all interstellar visitors. The dilemma sharpens when we consider humanity's history. Our greatest leaps often came when curiosity overrode fear. We crossed oceans, climbed mountains, sent rockets into orbit. Each time the risks were immense. Each time the unknown loomed. Yet without those risks, there would be no progress. Containment would have kept us safe, but it would also have kept us small. The same pattern applies now. If Atlas is harmless, then containment leaves us ignorant. If it is dangerous, curiosity may expose us to harm. The trouble is, we cannot know which until it is too late. The worst-case scenarios exist on both sides. If we choose curiosity without caution, we may provoke or expose ourselves to risks beyond imagining. A signal sent may trigger attention. An interception may be misinterpreted as aggression. Dust analyzed may contain seeds we cannot control. Curiosity unchecked becomes vulnerability, but if we choose containment, we may miss warnings, overlook threats, or pass by opportunities to understand our place in the galaxy. We may let probes observe us without ever realizing it, surrendering knowledge to caution. Containment unchecked becomes blindness. The balance is delicate, and the consequences of leaning too far in either direction could shape our survival. This tension is amplified by our disunity. Humanity is not one voice, but many. Some nations may push for aggressive study, others for cautious restraint. Private groups may act independently, sending signals or launching missions regardless of consensus. Curiosity and containment are not abstract. They are divided across cultures, governments, and individuals. A probe passing through our system does not face a unified species. It faces fractured impulses, some eager, some fearful. To an observer, that division may be more revealing than our choice itself. It may show us as indecisive, conflicted, unpredictable. And unpredictability is dangerous in any encounter. The possibility that Atlas is natural complicates the dilemma further. If it is only ice and dust, then containment looks like wasted caution. If it is more, then curiosity looks reckless. But the ambiguity is permanent. We cannot resolve it with certainty. Every interstellar visitor will force us to make choices without answers. Do we study, or do we shield? Do we risk knowledge, or risk ignorance? The paradox is that both options feel wrong, and both feel necessary. Consider the consequences if containment dominated. Humanity might adopt a policy of non-engagement with all interstellar objects, refusing active study, ignoring anomalies, letting them pass unchallenged. This would preserve safety, but at enormous cost. We would lose data that could reshape our understanding of planetary formation, of chemistry, of life itself. We would deny ourselves the chance to confirm or refute suspicions of probes. We would live in deliberate blindness, safer but smaller. Curiosity would wither, and with it, the drive that defines us. Now consider the opposite. If curiosity dominated, humanity might decide to investigate every visitor, to chase them with probes, to broadcast signals toward them. The risks would be significant. We could expose ourselves to dangers we do not understand, alert watchers who prefer silence, provoke responses we cannot anticipate. Knowledge would expand, but so would vulnerability. Curiosity without containment could lead us into traps we do not recognize until they close. The danger is that we might not know when we have crossed the line from boldness into recklessness. The truth is that neither instinct can be abandoned. Containment and curiosity must coexist, but the balance is fragile. Every visitor forces us to weigh them again, to argue again, to decide again. Atlas is only one example, but it sharpens the dilemma. Its anomalies make it impossible to dismiss. Its ambiguity makes it impossible to resolve. We cannot contain without wondering. We cannot wonder without risking. The two are inseparable, and that is what makes the dilemma so heavy. The worst-case scenario is that the galaxy itself is built on this tension, that every civilization that survives faces the same choices, the same risks, the same debates. Perhaps the silence we hear is not absence but consequence. Civilizations that chose curiosity and were destroyed, or civilizations that chose containment and faded into irrelevance. Perhaps survival lies in finding the balance between them, a balance we are only now beginning to test. If so, then Atlas is not just a comet or a probe. It is the catalyst of our first true trial, forcing us to confront instincts older than ourselves, instincts that may determine whether we endure or vanish. And so we watch Atlas, pulled between wonder and fear. We measure, we speculate, we argue. Our curiosity drives us forward. Our containment holds us back. Neither wins, neither loses. The object continues on, silent, indifferent to our debate. It does not reveal whether curiosity will save us, or whether containment will. That choice is ours alone. And it will not end with Atlas. Every interstellar visitor will reopen the dilemma, every anomaly will reignite the tension, every silence will force us to choose again. Containment versus curiosity is not a temporary conflict. It is the condition of being a young species in a galaxy we do not understand. From the moment Oumuamua first passed through the solar system, speculation has circled around one haunting question. What is the worst-case scenario? Each interstellar visitor has brought us closer to that question, and with 3i Atlas, the weight of it feels heavier than ever. We ask it as though there will be a single answer, a clear and frightening outcome we can point to and prepare for. But the truth is more complicated. The worst case is not a single event. It is not invasion, destruction, or even extinction alone. It is a set of possibilities, layered and interwoven, each one unsettling in its own way, each one pointing to a universe very different from the one we want to believe in. To ask what the worst case really means is to accept that it may already be happening, and that we may already be part of it. One version of the worst case is simple, that Atlas is artificial, disguised as a comet, and that it watches us even now. If this is true, then the worst case means we're not alone, and not in control of that discovery. We're being observed, catalogued, and judged without our knowledge or consent. The implications stretch beyond curiosity. To be observed is to be vulnerable. It means that another intelligence already knows who we are, what our world contains, and what stage of development we have reached. In that sense, the worst case means we are already known. And knowledge is power. Another version of the worst case is darker still, that Atlas is not simply a watcher, but a mechanism of containment, that it represents the reality behind the silence of the galaxy. In this view, every civilization that emerges is noted, monitored, and perhaps limited, never allowed to expand freely, never allowed to disrupt the balance of silence. If so, then the worst case means we live not in an empty galaxy, but in a managed one, a galaxy shaped by rules we do not know and cannot break. Our future would not be ours alone to decide. Our destiny would already be circumscribed by forces older and stronger than us. There is also the possibility that the worst case has nothing to do with intention and everything to do with chance. That Atlas is natural, but that its anomalies reveal just how little we understand about survival in space. If a body can endure billions of years in interstellar chaos, then perhaps life itself is far more fragile than we imagine. Perhaps we are rare not because intelligence is rare, but because persistence is rare. In this interpretation, the worst case means the galaxy is indifferent, hostile and empty, not by design, but by attrition. Civilizations collapse before they can endure. Atlas survives where life cannot, a reminder that matter endures, but minds do not. To realize this is to see our own fragility reflected in its passage. Another layer of the worst case comes from biology. If panspermia is real, then every comet may carry seeds of life. But if deliberate panspermia exists, if probes like Atlas disperse biology by design, then the worst case means our world is not ours. Our biology may not be purely Earth's, but a product of ancient seeding, engineered across countless systems. We may not be unique at all. Our DNA may be the result of programming written long before us. In this view, the worst case is not death, but manipulation. That our existence is not by chance, but by design we cannot see. Design carried out by relics drifting through the dark. Atlas becomes a gardener's tool, and we become the garden. The horror here is not destruction, but the stripping away of agency. We are no longer authors of our story. We are chapters in someone else's. There is also the subtle worst case of irrelevance, that Atlas is artificial, that it does watch, but that its conclusion is simple. We do not matter. That our species, our signals, our industry are only a data point in a record already overflowing with others. To us, discovery feels monumental. To it, it may feel ordinary. The galaxy may be filled with life that rose and fell long before us, civilizations that shone brighter, spread farther, and vanished more completely. In that comparison, humanity may not even rank as notable. The worst case here is not threat or manipulation, but dismissal. That we are not important enough to matter to the watchers who pass, that our existence is not special at all but routine. And yet, another possibility takes the idea of routine even further. What if Atlas is not unique, but one of many? What if probes pass constantly, all disguised, all watching, all recording? Then the worst case means not that this is extraordinary, but that it is normal. That we live in a galaxy where surveillance is constant, where every system is catalogued, where every civilization is observed from its first sparks to its final silence. The presence of Atlas would then not be revelation but confirmation. It would mean the worst case is not a future possibility, but the present reality of the galaxy we already inhabit. The human mind resists these possibilities because they strip away the illusion of control. We like to believe that the future is ours to shape, that exploration is ours to begin, that discovery is ours to claim. But the worst case scenarios suggested by Atlas all tell us the opposite. They tell us that our future may already be decided, that exploration may already be mapped, that discovery may already have been made by others long before us. They tell us that our role may not be to explore the galaxy, but to be explored by it. The worst case is not only what Atlas might be, but what it says about us, that we're late, that we're ordinary, that we're not in control. This does not mean catastrophe is inevitable. The worst case is not necessarily apocalypse. It may be slower, quieter, more insidious. It may mean that humanity continues, but never beyond a certain point, never beyond containment. It may mean that we expand, but only along paths already set for us, unaware that we are following designs not our own. It may mean that our biology carries seeds of other civilizations, that our history is part of a cycle older than our species, that our choices matter less than we think. The worst case does not need to end with fire. It may end with silence. And silence in its own way is more frightening. What makes this question unbearable is the fact that we cannot resolve it. Atlas will pass. It will leave behind data, numbers, spectra, papers. It will leave behind debates, suspicions and fears. But it will not leave behind certainty. We cannot know whether it is natural or artificial, whether it carries life or death, whether it watches or ignores. The ambiguity is permanent, and that ambiguity is itself the essence of the worst case. To never know, to always doubt, to always suspect but never prove, that is a condition that may stretch across every interstellar visitor we ever see. The worst case may not be one outcome, but the perpetual inability to resolve any outcome. We will always wonder. We will never know. If that is true, then what the worst case really means is not destruction, not invasion, not manipulation, but endless uncertainty. We will live with questions we cannot answer, fears we cannot confirm, suspicions we cannot dismiss. We will see more visitors, more anomalies, more silences. Each one will deepen the debate, sharpen the tension, expand the possibilities. Each one will leave us with the same haunting ambiguity. The galaxy will remain quiet, and in that quiet we will hear echoes of everything we fear. The worst case is not what Atlas is, but what it makes us realize about ourselves, that we are too young, too limited, too fragile to ever know the truth. And so Atlas moves on, another fragment of light fading into distance. It may be comet, it may be probe, it may be ghost. We do not know, and perhaps we never will. What the worst case really means is not that we are doomed, but that we are left forever in between, not certain, not ignorant, not safe, not doomed, only suspended in ambiguity, searching for answers in silence, knowing that silence may be the only answer we ever get.